Good morning, everyone. It is our great honor to welcome you all at the first ever national conference on Magmatism, Metamorphism, and Metallogeny in India, hosted by National Center for Earth Science Studies, Ministry of Earth Sciences. This landmark event brings together esteemed scientists, experienced faculties, and young researchers to discuss the latest advancement in magmatism, metamorphism, and metallogeny, the three most crucial part for understanding the geological evolution of the Indian shelf and its enriched mineral resources. To begin the inaugural function, we invite our esteemed dignitaries to the dais. Director ESSO-NCESS, Professor N.V. Chalapati Rao, the driving force behind this initiative. So please come and take your seat in the dais. Professor Talat Ahmed, RAC Chairman, ESSO-NCESS, and an eminent geoscientist known for his contribution to petrology and geochemistry. Professor Somnath Dasgupta, former RAC Chairman and a pioneer of advancement in metamorphic petrology in India. So please come and take your seat. Now I invite Shilpa, Haripriya, and Vidya Lakshmi to present a flower as token of welcome. Now, to officially commence the event, we invite Director ESSO-NCESS, Professor N.V. Chalapati Rao, to deliver the introductory address and share the vision behind this conference. So please come.
Thank you, Dr. Sneha. A very, very good morning to each of you, your accompanying persons, for this very unique and inaugural conference on three big M's in Earth System Science: magmatism, metamorphism, and metallogeny, of course with the focus on the Indian shield. Professor Talat Ahmed, the RAC chairman and renowned igneous petrologist and geochemist, Professor Somnath Dasgupta, former RAC chairman and the man who was responsible for drafting the constitution for merging CESS with ESSO-NCESS a decade ago. And it's very fitting that these two people who are associated with CESS from the beginning are today with us. And along with, we have so many galaxy of scientists in encompassing these three fields. Here, just, I'll just pick up few from what I see: Hetu Seth, Sen Sharma, Rajesh Srivastav, Shantanu Bhaumik, Krishnamurthy, Shaibal, Dr. Balram, Venkatesh, and so many people, young people, seniors. I welcome each of you to this August gathering. Now, let me share my thoughts on why this conference had to be organized and the purpose behind it. Now, we all know that in the Earth System Science, and that too in geosciences, solid Earth is a very, very important component. When a student joins geology, the very first course he attends is mineralogy, and later on others follow. So there is no doubt that the importance of solid Earth is there from the beginning of the geoscience, and it still continues. You see, some of the most fundamental questions in Earth science, like how planet Earth has formed, what's its relation to other planets in our own solar system and beyond, how mountains form, how plains form, how oceans evolve, how plume tectonics or plate tectonics happens, how it happened through the geological time, how accretionary and collisional orogens form, what is their actual significance. I mean, these are some few thoughts. How metallogenic epochs and provinces are formed, what's the rationale behind it. All these come under these three very, very important branches of our 3Ms or M cubed. That's one aspect which many of you are aware of. Now, if you look at the contemporary Earth sciences, you know, technology is driving the science in a way. When we studied, we were taught that only three isotope systems were there: strontium, neodymium, and lead isotopes were applicable, and that too on a whole rock scale in 90s, early 90s. But today we know so many isotopes which are there can be measured. So our solid Earth has been revived, in my opinion, due to technological advance to a great extent. And what was not possible few decades ago and even 10 years ago or 5 years ago is now possible now. So now our students, the future generation, should be made aware of these aspects because they may be under illusion that solid earth may not be so, our 3 branches may not be so exciting. So this is one of the rationales behind starting this series of these conferences. Second, if you look at some of the major missions of Government of India, most of them sponsored by Ministry of Earth Science and Ministry of Mines. You look at Deep Ocean Mission, you look at Chandrayaan-4, which is coming up. You look at the critical minerals about which our Prime Minister talked only yesterday in United States, lithium and all. That means there's a great resurgence in all these missions and requirements due to the need, geopolitical needs. And we need to encash these, we need to take up. If we, our 3 groups and their practitioners, if we don't take up, who in India is going to take these up? In Deep Ocean Mission, Ministry of Earth Science is targeting the marine resources, your hydrothermal sulfides, polymetallic nodules. You know, 1980s, there was a huge rush to sample polymetallic nodules, but not much headway could be made because technology in those times was not that good. But today, we can recover them with, great values can be recovered out of the polymetallic nodules and precious metals. In Moon, 1969 Apollo mission has brought the samples and a lot of work has been done. And today's understanding of whatever we know of how solar system has evolved is based on those samples. And Chandrayaan, our own country, is launching machine and our institute is also involved in it to work on the samples. So where our solid earth 3 groups come into the picture in a great way. So that's the second rationale behind having this conference. And the third thing was, when I was doing my PhD, Shaibal and all, we were there and we used to participate in conferences, specialized conferences, like Magmatism and Volcanic Studies group used to be there. Every year, the people who are in Great Britain and surrounding areas, even from Europe, used to go there. The youngsters especially used to showcase their findings. It's an annual mela. In Metamorphism, there was a Metamorphic Studies group. And in Metallogeny also, there used to be a group. But these specialized groups are very important, I feel, because the youngsters will be given a very good feedback by their own peers. Okay, there are so many conferences where a multi-faceted people will be there, and that is fine. But in a specialized conference, like specialized journals, I believe, you get the best of the feedback because your own field people are there. And also, as youngsters, and even now we feel very excited when we meet people in person whose works we have read. Even I feel very excited when I meet a person whose work I read but I never had an opportunity to meet him, and surely for young people. So we thought this type of conference is needed where these 3 groups can be brought together. You see, where igneous stops, where metamorphism begins, or where metamorphism stops, igneous start, these were the things which were addressed in the early parts of the last century. But today, nobody is talking in these terms. Today, we are talking about a transdisciplinary, interdisciplinary, and so unless we 3 groups forge together, work hard, and come up with bright ideas, we cannot tackle anything. That's the reason why I thought all 3, including metallogenesis. 90% of metallic mineral deposits are from igneous processes only, and also from metamorphism like graphite deposits and all corundum and precious stones. So metallogenesis is sorry to say, is a metallogenical research in India is almost becoming an extinct species, and it is our mandate to revive it because government also is mandating that. So, and I also notice there are different forums in India on these lines, like micropaleontology have a forum, sedimentologists have a forum, and our structural geologists forum is working very well. So I was thinking since decades that we should have one. Myself and Rajesh, we had discussions at BHU, but you know, for everything there is a saying time should come. So when I joined, I got an opportunity. I thought, why not start this one, this type of thing, along with an women's conference, which we did a few months ago. So that's the background behind bringing all of you here. And I'm very thankful and grateful to each of you and those who are also viewing this program online. We have made it live, 3 days live program we have made it, because one of my colleagues suggested you are doing a lot of good programs, let it be benefited to whole India. So we thought unless somebody has any strong reservation, we can stop that for their presentation. But all programs are live, and we have advertised also, because science should be disseminated far and wide and beyond boundaries also. And I should tell you, when we started this, there has been unprecedented response. You can see we have people, 125 abstracts, so many people came up, we could not accommodate many. We have another satellite room, which is there next. Actually, our main auditorium is under renovation, which has a 200 capacity. It would have sufficed the cause. But then we thought we cannot wait for it, let us move ahead. So we thought we are here to do science, little bit of compromise we can make. The more important thing is to do science, meet people, and share ideas. So some of our colleagues, delegates are also sitting in the next room live. And for question answer also, they can interact from there. And if they want, they can run out and ask questions from here. That's because they are all very young. Now I should also say a few things about ESSO-NCESS, because we are here. I feel very proud to be a part of National Center for Earth Science and Ministry of Earth Science family. You know, ESSO was started in 1978 by, again, a very visionary geologist, Karunakaran, who served as Director General of GSA. Upon retirement, the Kerala state government has invited him to start a center. And he envisaged earth system science, your atmosphere, your oceans, your planetary system, your solid earth, of course, and hydrosphere together to start an institute center for earth science studies. And I should tell you, if you look at the legacy of ESSO, many stalwarts served here in the initial batch, which was recruited, because the initial batch in any institute or university, it is a make or break. Whether their destiny of future depends on the persons, and especially the first batch. And many good people were recruited, and some very good could not be recruited also. So somebody will tell about that later on. But that set a legacy for 80s, 90s, even 2000s. ESSO was one of the leading earth science departments, institutions in the country. And so many papers came up in very good journals. That's how an institution should be actually evaluated. In earthquakes research, in reservoir-induced seismicity, landslide research, in mafic dike swamps and paleomagnetism, and the metamorphic systems. Very good papers, very leading scientists were involved, fluid inclusions. M. Santosh was here, T. Radhakrishna, Kusala Rajendran, C.P. Rajendran, Harsh Gupta served here as the director, M. Ramakrishnan, Subimal Sinaroy. I mean, so many names with everybody. Seniors are familiar, and I'm sure young people also will be familiar when you go through literature. They all worked there. Now, in 2014 was a very defining moment when ESSO was taken into the ambit of national government, central government. Ministry of Earth Science has taken it, seeing its promise, because Ministry of Earth Science was having labs like NCPOR, INCOIS, and many labs, but solid earth component was missing, and they thought it should be taken into their fold, and that's a defining moment. Then we became a part of the central government. Now, becoming a part of central government is important because your funding has increased. I mean, your opportunities have increased, exposure has increased, and ESSO, as today, as it stands, it works in 4 or 5 big areas, thrust areas. One is solid earth itself, where our institute, I can say very proudly, is now heading the in situ geochronological development in the country. We have MCM, ICPMS, we have laser ablation ICPMS, multi-collectors and all. We are publishing very good papers. In last 2 years, our scientists have published 12 papers in pre-Cambrian research indigenously, without collaborating with any foreigners. We have a very strong geophysics group. People have worked on gravity, your resistivity, and also seismic. And they have published papers in Earth Science Reviews on Indian Ocean Dipole, Indian Ocean Geoid. And our geophysicists also worked on gravity modeling of rift basins, Godavari and all. They published in journals like JGR, Solid Earth, and Geophysical Research Letters in last 2-3 years. And we also have people working in atmosphere, lightning, cloud microphysics, and lightning, how lightning can be used to predict monsoons, and also aerosols. We are entering into it. We have a small group, but it is very vibrant group. In environmental hydrology, our scientists are doing tremendous job. They are working on major river systems. We are working on geothermal resources, how this groundwater is getting warmed up, what is the age of the groundwater. They are using different techniques to understand this process. ESSO-NCESS is also credited for the submarine groundwater discharge programs in the country. We know that marine water incursions, seawater incursion on the freshwater aquifers happens, but there is also a less understood submarine groundwater discharge, which our scientists have understood the hydrology of it, and it is the leading organization in the country with help from a lot of institutes, including IIT Kharagpur, IISc and all. These programs ESSO-NCESS has done. In coastal mapping, coastal erosion management and all, ESSO-NCESS has been pioneer from the beginning. You know, when Karunakaran took over, he thought science should be immediately applied to the society. So he always felt that unless we are taken seriously by society, state government institute with limited funding cannot survive. And that legacy is still being continued. Our maps prepared by our scientists on coastal zone erosion and all are taken in toto by state government, central government, and also by legal authorities also. If you want to construct something, then you need to have permission from ESSO-NCESS report, whether it is really worthwhile or not. Because a lot of geoheritage sites like Varkala, you all know they are there in the news. So ESSO-NCESS has been working in all so many diverse areas, but having said that, our main mandate is your solid earth. So we have very vibrant scientists. Our average age is around 42. Leave me, myself and 2-3 people who are above 50. The average age of the institute is 40, very young institute. We have people from, say, Kashmir to Kanyakumari, all India nature. Very good analytical facilities you will see, and publication record. I can say very honestly, I was surprised when I joined. These people are doing tremendous job, and I feel very happy to be associated with them. So these are few things which come to my mind, and I am sure this conference is going to be a very landmark, because we want to have this conference not as a one-timer, but it should continue. Every year it should be held at different places. Then we can have a EGU or Goldsmith conference here when such a society is there. We should aim big, and why not? No, this is the time to hope big and aim big. I'm sure dreams can be realized. And we try to gather the best of the people and the most promising of the youngsters, and I'm very happy again to each of you for making it here. And I'm sure you will have a very great time, not only in the conference, but in the lovely city of Trivandrum, the city of Ananta Padmanabha Swami, holy city, God's own country of Kerala. And I am sure you will also take some time out to later after conference to go around city and enjoy the beauty. Thanks again, and I now ask Sneha to take over. Thank you.
Thank you, sir, for your insightful words and for emphasizing the significance of this conference in such a way. Now I invite Professor Talat Ahmed to formally inaugurate the conference and share his thoughts regarding this.
Thank you very much. So I have this great pleasure to be here. And first of all, let me officially inaugurate this function. Although the Secretary MOES was supposed to be here, but because of some reason, an assignment, he could not come. So officially, we declare this conference on. Now, as Chalapati has told, and we could see that slowly all these M-cube subjects like igneous petrology and metamorphism and mineralization or mineral aspects, it has gone down, or maybe it is not very popular, okay, unfortunately, although it is the real geology from where you can actually start. And you can see particularly now with the emphasis and the importance of all these mineralizations, particularly lithium, as he said, and then the critical minerals and many other minerals, I don't see many activities in the country, particularly the leading. I am very happy to see Venkatesh here as one of the torch bearer for mineralization aspect. Or maybe some other people, but similarly in Delhi University, such an old department, Mihir Dev used to be there, and now there is nobody. No, but not here. I'm telling, he will be coming. Yeah, so that's very nice. So similarly, igneous petrology, of course, Chalapati is there, and Rajesh, and many others, and then metamorphism is still the Somnath group, and Bhaumik, and others. But most of it, they go in isolation. Now, as we know, that everything is connected, and particularly I think the metallogeny and mineralization aspect needs to be concentrated more. And it is not only igneous or metamorphic rocks, but also the sediments where they go and get deposited and get enriched and things like that. But unfortunately, although we have big forum of sedimentologists and sedimentary studies in the country, but most of them have become environmental scientists or climate person, to talk about climate change and things like that, rather than really looking into the geology and the mineralization aspects of sedimentology. In this country, we have lots and lots of big sedimentary basins, okay? But very little information is available in terms, although GSI and all, they keep doing the regular mapping and things like that. So this sort of conference, I think, is very important and very timely. So I congratulate both Chalapati and Rajesh that they thought about it. Rajesh is always thinking about these things कि लोग पहचानने कि भाई हम लोग भी हैं दुनिया में. Okay, so from that angle it's good, and they have started this, and I'm very happy. Another important thing is that many of the old senior people I keep meeting, but many of the youngsters, or not even youngsters, 20 वाले एज के भी काफ़ी लोग हैं जो बहुत कम नजर आए या मुलाकात हुई. Okay, so and then the youngest who are sitting in the other room, उनको तो मुलाकात ही नहीं होती, वो बेचारे सिर्फ चाय वाय में कहीं पर नजर आते हैं कॉन्फ्रेंस में. But the good thing is, I was talking to Chalapati last night that we are going to have lunch and dinner also here. So we should have enough opportunity for the youngsters in particular to talk to people. Don't feel shy or don't feel afraid. In fact, we are all here and we have to give. We have done our job, whatever we could do, good or bad, but we are here and we have some experience. So try to get as much as possible for future of the country, okay? Because you are the future. And metallogeny and igneous petrology also, I would say that as you know, it has become very, very sophisticated from the time that we did work and now, okay? So our teachers in the university should also brush up and come to the level of what is expected now to be an igneous petrologist or teacher of igneous petrology. Forget about isotopes, even I am very sure most of us don't know what are trace elements and how it works and what is the importance. So all these things the teachers have, because ultimately these teachers will produce the students, and if the teacher doesn't know, he will also produce the same sort of students. So we need lots of changes, and this is very, very timely. We should not feel shy that things are not what we should have had by now, but other countries are doing, so we have to do it. In terms of the mind and brain, we have excellent in this country. The only thing is, we should have, the environment which encourages more research, good teaching, and good opportunity for all the youngsters to grow. Only then we will be successful, as a geologist, and particularly this M-Cube group in M cube. Okay, so I really am very happy to be here and associated with such a good and renowned organization of this ESSO-NCESS. And I am sure that the start that Chalapati and Rajesh has started, so I understand, and he says that we should do it at least every year, one conference. So maybe, obviously, after ESSO-NCESS, Rajesh, किसी को और chance नहीं देंगे. So let it go to BHU next year. But for the third year, I am at Vardia Institute, so I say we will be very happy to have it in Vardia. But the thing is, I was also told that some of my friends, because I have lots of friends all over the country, so NGRI वाले हमसे बड़े हैं. तो अगर वो खींच के ले जाते हैं, तो maybe after that. But we will be happy to do it at Vardia. Okay. Whatever little we have contributed in terms of the igneous petrology, metamorphism, and mineralizations, we will write. Although I know that mineralization is high, because hardly we have done much. Okay, so we need to bring these conferences to different places and make it popular among the youngsters. So I think these are some of the thoughts, and then obviously, as I said, it is more important for us to interact with the youngsters. We are available. मेरी बात जब थोड़ा कम सुनाई दे, because I have problem of dryness in my mouth, so I keep taking water. But I will be happy to have this water in my hand and talk to anybody who wants to talk. Okay, and same thing I can assure about Somnath and all the seniors. So I congratulate you, Chalapati, and ESSO-NCESS, and obviously Rajesh, and all my friends who are in the first row, and my other friends in the second row, and obviously the youngest in the other room. Thank you so much.
Thank you, sir, for your inspiring words, especially for the young people, and inaugurating this landmark event. A conference of this scale is incomplete without a compilation of research contribution, and it is our pleasure to announce the release of the abstract volume. To mark this occasion, we request Professor Talat Ahmed, Professor Somnath Dasgupta, and Professor N.V. Chalapati Rao to jointly release the abstract volume. Thank you, sir, for unveiling. Another good news, one book is coming, publishing from Geological Society, special publication, that on alkaline rocks, economic and geodynamic significance through geological time, edited by Rohit Pandey, Ashutosh Pandey, and other people. Sir, I will request you to release the flyer also.
Geological Society of London special publication, which is coming in.
Next, we invite Professor Somnath Dasgupta to share his general remarks on this objective and impact of this conference.
Thank you, Sneha. So, good morning, everybody. Like our RSC chairman, I also have a problem of dryness in mouth. I think we share the same fate.
They are all metamorphizing.
So, excuse me if you cannot understand some parts of my talk. The issue is, I was trying to interrupt Professor Chalapati Rao to leave something for me. So he didn't leave anything for me. And Professor Talat Ahmed also told about the future problems. So what shall I do standing here? Because every aspect has been covered by these two speakers. In any case, the first thing is, it's my probably 40th year of visit to CESS or NCESS. So right from 1980, I am visiting this place. So I have seen the transition at every stage from when it was a very small department in the state government, CESS, and then transferred to NCESS in 2014. So we started planning, I think, from 2013 or 12. Actually, the leadership was taken by Professor Shailesh Naik, the then Secretary of MOES. And many of us drafted the constitution, and it was a difficult job to do that. In any case, we accomplished, and I was given charge of the first RSC by MOES. I served here for 5 years RSC, and I faced the biggest problem then was that the average age of the institute, it was so high, almost 55 or so, and everybody retired very soon. So we had a real problem. But then gradually now I see that the average age has gone down to 42, as the director said. So it means that we have accomplished the first stage, that have brought down the average age. So there are a lot of youngsters here, and MOES was very generous in funding. So we have perhaps the best analytical facility in the country, and it is a completely functional analytical facility. That's the important point. So we have at many places analytical facilities, but they are not in only name. Here, everything is functioning thanks to this group of people sitting here, that everything is working. I have been benefited personally as well, so I can vouch for that. So the critical thing for the director to plan now is how to optimize the use of these instruments or maximize the use of the instruments, how to involve other people working in different corners of the country so that they can make use of the instrument and make real good scientific joint programs which will bear fruit in the future. So this is something that I think the RSC chairman is very competent, Professor Ahmed, will definitely help Professor Rao to formulate a strategy that how to utilize it further better. Because the sky is the limit, so you can always increase the quality. That's one thing. So NCESS, I'm very happy to be here in NCESS today under the dynamic leadership of Professor Chalapati Rao. It has really, really moved, it has come into prominence that everybody see, not only in social media, but in real sense. Of course, I know that with the present director, I am possibly on the social media right now. He's so fast. But I think that's one of the aspects of the modern day, that how we work. In any case, that's part of the NCESS. Now comes the question of this conference. People have said that this is for the young people, by the young people. We are just catalysts. We started it, okay? Talat has already said next year it is BHU, Karsi Rajesh, followed year. And the next year, there's a stiff competition between Wadia and NGRI, Raman and Talat. I don't know who will win. In any case, one of them is fixed. So 2 years fixed like that. 1, 2, 3 are done. And the 4th year, our director, Chalapati, has said that he wants to wind up his directorship with the further conference here. So it means that we have 4 years in vision now. Now the question is, it is left to you then to carry it forward. So after that, this generation, I think, will vanish. So, so the next generation, you people have to take it up and take it forward and to make it sustainable, because sustainability is the key word that we talk in every forum. Now, the only new thing I would say, add to this is all people have said, but one new thing that came to my mind to say that we welcome the other groups to join us. We will not join them, they should join us. For example, the sedimentologist group or the structure tectonics group, they should join us. So actually the solid earth sciences have 2 more components, they should come together. And so if we can really make it a kind of a solid earth community, that will be even better. But to start with, I think this is a big thing that they have done. And I was personally very enthusiastic when Rajesh and Chalapati, actually they were planning initially with only magmatism. So we pitched in together, pushing metamorphism there, and then they thought that why not bring metallogeny. So that way we 3 are here, but the question is that we need more. And the next conference onwards, I would request the organizers to give more platform to the youngsters for presentation, talk, that we should be there, but the main thing is to just on the advisory capacity, but the youngsters should be given more time to talk and not poster, talk also. Posters will always be there, but some more talks. And in any case, this is a new horizon that has opened up in front of you today. And I do hope that you will carry the torch forward. We will not be able to do that. You have to do it. So I hope that you will take it forward. And I, of course, wish a grand success, not only of this conference, but the conferences which will come in the future. And I don't know how far I will be witness to those conferences, but nevertheless, I would like to see the next 5 at least to set the ball rolling. After that, you people take over. And I think that is all that I have to say. Thank you very much for inviting me here. Thank you.
Thank you, sir, for your valuable insights and for emphasizing the significance of this solid earth community. As a token of our gratitude, we now invite our director to present mementos to our dignitaries, Professor Talat Ahmed and Professor Somnath Dasgupta. Thank you, sir. With this, we conclude the inaugural function of the National Conference on this Magmatism, Metamorphism, and Metallogeny, and extend our deepest gratitude to our esteemed guests and participants for making this pioneering event possible. Now we will, as we move ahead with our technical session, we hope this conference will set a suitable network and sustainable research network in the field of MQ. Thank you, sir. Now it's time for tea. Tea is arranged in the outside. Please have a tea. And our technical session, we will start from 11 a.m. Thank you. Yeah, here only, just outside the room. Tea is arranged.
Then you have Sukanta Day is again here from, Sukanta is here. And Simo Tini, Sen Sharma, कल मेरे साथ ही आई थी हाँ यही तो है ये है and then Indrajit is also here. So I will ask Hetu to conduct this, but I will be around. Okay, so Hetu, please go ahead.
Okay, thank you, Professor Talat Ahmed. Okay, now I would just like to say a couple of things. Please stick to time because we are following time very well. I would request the first speaker, Professor Rajesh Srivastava, to give his talk. And 3 minutes before the talk ends, I will get up, and then that is the time we should have for question and answer. Okay? So maybe have a couple of questions. So this is very important. Thank you, Professor Rajesh. Over to you.
Thank you. Thank you, sir. Good morning to all of you. So MQ started now. So as you see, that topic is that analogous mental plume derived magmatism on the Earth and Venus. So my purpose that we are doing mapping of Venus surface. So how these are matching with the Earth's grabens or our diaphragms. That is the main theme of this talk. बढ़ नहीं रही है? Yes, yes. So this is a part of a group, international group working on the mapping of the Venus surface, and that group involved many countries. And it is thought that Earth and Venus are the twin, so in size, but they are different in many things. So that Venus does not have plate tectonics, no surface erosion. 80% is covered by volcanic activities, that basaltic flows, and the temperature is very, very high. So, but there are some similarities also, particularly they have igneous activities almost similar of kind. And this is important in view of that recently government has declared that Sukrayan, so that will be take place in March 28, 2028. So that way it is important, and its objectives are very much related to Earth system science. So particularly I am interested in that investigate surface processes or just mapping the surface of the Venus. We can't go to Venus, but with the help of technology, we can map the Venus surface. And this is further important because Venus was thought that when it was formed, then there was water, but now there is no water. There was ocean there on the Venus, but there is no water. So why it happened that it is too hot? That surface temperature is 470 degrees centigrade. So that is very crucial. And whether if this condition happened with the Earth, so Earth can also be a fireball in future. So that studies are important. That's why that Indian government is sending Sukrayan to study the environment and surface of the Venus. So if you say that large igneous activities or large volume igneous magmatism, that we also known as large igneous provinces, LIP. So there are three main things actually. That large igneous provinces for the youngsters actually, the senior people already know what is LIP, but for students, that it should be a huge volume magmatism, and of the short duration, up to the 5 million years duration maximum, and it must be an intraplate intraplate setting. So, and that example is, that Indian example is Deccan volcanism, this very well known Deccan volcanism. It has a huge continental flood basalts and dike swamps also. But there are plumbing system also. If you go to Precambrian age, so that volcanic flows are eroded. So you don't have volcanic flows. So that plumbing systems are important to identify the large igneous provinces. So that includes that large dike swarms, sill complexes, mafic, ultramafic intrusions, and there are some silicic LIPs also. I'm not going in detail. And carbonatites and alkaline rocks, kimberlites, they are also associated with the large igneous provinces. Deccan is best example. If you say that 65 million years old Deccan volcanism, they have that has kimberlites also, carbonatites also. Ambadongar is famous carbonatite complex associated with the Deccan LIP, and many kimberlite occurrences also associated with the Deccan LIP. And if you go to Archean in age, so greenstone belts are the main candidate for the identifying the large igneous provinces. If you have a cometite tholeite association, so that is the cometite is thought to be intraplate tectonic setting magmatism. So that is also a clue to have to know whether there was a LIP or not. Many layered complexes also is associated. And this is the cross section, and you can see this flood basalt is here, huge, covering huge area, and this is very easy to identify the large igneous province, just like Deccan. But if this portion is eroded, so you have a plumbing system to identify the large igneous provinces. So magma generated due to plume, the plume head, and from the lithospheric mantle, and you have a magmatic underplating, the dike swarm, sill complexes. So many things, these are there. So particularly it is important for the Precambrian terrains, that's Archean Cratons. And we mapped all these dikes, the Precambrian dikes in the Archean Craton, and most of you can see this many dike swarms. Till date, we identify the 22 large igneous provinces, 5 in Archean, 13 in Proterozoic, and 4 in Phonerozoic. So these LIPs are very much emplaced in the Indian silt, and we map these swarms in detail with the help of Google Earth, geochronology, geochemistry, petrology, all field work also, because field work is important to identify whether these dikes are there or not only the Google Earth or something. So each Cratons are mapped in detail. And if you have this type of data, then you can identify the, for example, you can identify that with this trend, with the age, everything, you can identify the plume center also. I will come to that. So just to refresh you that 4 Phanerozoic large igneous provinces are Panjal LIP, the Greater Kerguelen LIP, Madagascar India LIP, and of course that Deccan LIP. So these 4 are during the Phanerozoic, and these 18 are during the Precambrian. Out of these 18, 2 are siliceous large igneous provinces, that mostly they are mafic in character, but they can be siliceous also. So this Dongargarh siliceous LIP, and Malani is well known slip occurrence in the Indian silt. So I'm not going to that, but purpose is different. And how it looks in field, that if you visit the Dharwar Craton, so these dikes are beautifully exposed, very long dikes are there. You can see these dikes are there. So you see all these dikes are running. And if you see the Google Earth, so even from the Google Earth image, you can observe the different dike swarms. This is the Bastar Craton, northern part of the Bastar Craton. The Panda is here, I think he worked on that area. So you can see this northwest dikes, so 2.37, this is different dikes. Some dikes are, you can see north-northwest, that is 1.89, 1.88 in age, and there is east-northeast dikes, that is 2.25 in age. So different dike swarms are exposed in the Bastar Craton. This is one part, just I'm showing that how we map these dikes. This is the Dharwar Craton. Again, you can see different dike swarms of different trend, different ages. This is Singhbhum Craton. You can see different trends and dikes, and they have different ages also. And based on almost all geological criteria, that Google Earth image, they are mapping, geochronology, trend of that dikes. So we identify different dike swarms in each Craton. This is one example, this is Dharwar Craton, and different dikes are identified, and their trends are different also. So there are many in Archean age and many are Proterozoic in age. some are undated also, that we are in process to date those swarms also. And based on these trends, they are linear swarms, particularly linear or radiating swarm, we identify the plume center of these swarms. So one example is 2.37, 2.36 Bangalore large igneous provinces that is exposed in the Bastar Craton as well as in Dharwar Craton, not in the Singhbhum, but we expect that these swarms must also be in the Singhbhum Craton. So, and there are two models are there, but this model is particularly also justifying the available paleomag data. So, there are some rotation in the northern block and southern block in Dharwar Craton, and it is thought that if you see the radiating swarm, they have the same age, 2.37, 2.36, and trends there, just this plume center was there to feed that dike swarm. So this is one thing, that if you have a radiating swarm, linear swarm, so you can identify the plume center of that event. Another example is that 2.26, 2.25 Ipaguda LIP that is exposed in all the three cratons. Recently, we also identify a mega craton called Dhabasi, Dharwar, Bastar, and Singhbhum. So they have many common igneous activities. So with the help of these trends, plume center was probably somewhere here to fed these dike swarms. Same thing on the Venus also. So if you see the map of Venus, that surface of the Venus, not map of the Venus, even you can observe that many linear bodies are there. And these are identified as the grabens. So these grabens are mapped. We thought that these grabens are expression of dike swarms. And volcanic flows are also there. But in first part, we are mapping the dike swarms. Second part, we will map the very easily, just like Google Earth. So that can be mapped, and that can be, the different swarms can be identified and events can be identified. So this is another area. You can see the different grabens and different trends. So with the help of Magellan SAR data and JMRs, we are trying to map the Venus surface. And as mentioned, that Isla Reggio is the portion where we are mapping. And thousands of grabens are mapped. Several thousands of grabens are mapped from this area. So if, just like Dharwar, Bastar, and Singhbhum we have seen, that is not in the Indian shield only. These dike swarms are exposed all over the world. So just I have taken, because I am working on the Indian shield, that's why I have taken the Indian examples. So you can see this, many grabens are there in the Venus, and all these grabens are mapped. And based on the trend, and that particularly trend and cross-cutting relation, because you can't have the samples to date them. So you can only based on that, you can that based on their trend. And there are, just I mentioned that one of the thing is that circumferential dike swarm. This is very crucial because very few examples on the earth actually. But these circumferential dike swarms are very crucial to identify the center of the activity, igneous activity. So, and then this is the generalized, that we have first we mapped the different grabens, and then we generalized, and with the generalized that we identify different swarms, that you see the 14 that radial swarms, and the circumferential 6 swarms. There are 16 linear swarms. So these swarms are identified based on this mapping. This is the Bella Eli area. This is the Gaya Corona, where we did the same thing. And then this is another area, this is Nehalenia Corona. So this is other mapping. And we published first paper in ICARS actually. So that is already published, that Chadha et al. So this gives you the different, if you see this, if you see this circumferential swarm, they are radiating swarm, that this C1 is a center for circumferential swarm, R1 just for center for the radial swarm. So that way identify the different centers that probably fed these dike swarms.
1 minute. You know, 1 minute.
1 minute.
2 minutes.
Okay. So
We need 3 minutes per question.
So anyway, so that this is the, on Earth we have a circumferential swarm. The best example is Lake Victoria. Just similar to the Venus, you have observed that circumferential swarm. And if you see the Indian example, Deccan is a good example, where we have a circumferential dike swarm besides the radial swarms. So, and again they have large, this is the Canadian field dike swarms, is very famous, these dike swarms. And you can see this huge dike swarms, and this is the center for these dike swarms. Same way the Gulamans having the, you can see the large dike swarms there. So that way we are comparing the available Earth dike swarms with the Venus surface dike swarms. And, sorry, and that with the help of cross-cutting relation, this is Dharwar Craton, with the help of cross-cutting relationship, which is also available on the Venus, we identify the relative ages. We don't have a number, but relative ages are done. So this is the younger swarm, this is the older swarm, and based on the cross-cutting relationship, the sequence of emplacement on the Venus is also identified. And also with the help of the circumferential swarm, we also try to have to know the size of the plume. So size of the plume is also calculated. So just I wanted to convey this message that Venus has very similar magnetic activities as our Earth has. Thank you very much.
Thank you, Professor Rajesh. Very interesting presentation. We have time for 1 or 2 questions.
Yes, please.
What students should be asking, but just to set it off, just your dikes in the Dharwar, Bastar and Shingbom, you showed a plume head which you suspect that was responsible, right? Below, to the south-west of Bastar, I think, that's where you showed a plume.
Yes.
The suspected plume
Yeah,
source.
that based on the radiating swarm. Yeah.
But I was just wondering the way the dikes are in the 3 Cratons, why are they so systematically different in the 3 Cratons if it's from one plume?
No,
Like as per your map
Yeah.
with the dike
because we have
trends.
to also justify the paleomag data.
And
So-
why are the trends different? The orientations of the dikes in...
No, because they are radiating swarm. That suppose if you have a plume, in one Craton it may be like this, other Craton it may be like this, other Craton it may be like this. So these radiating swarm joining somewhere. So that is the plume center there.
Okay.
1 more question.
Sorry again, students should be asking. Anyway, you showed the swarms in one particular Craton, let's say. They're in different directions and you have different ages
Yes.
for that.
Yes.
So what's the age of the plume?
Age of the plume almost the same age as the dikes.
So there are multiple plumes.
Yeah, multi-plumes can be. It is there, multi-plume.
Because you have
yeah,
quite a spread in age.
Yeah.
So multiple plumes.
Yeah.
Okay. Fine.
Is it a multiple plume or there is a long duration plume here? So that will be
That is a
completely
big question.
different.
That long duration plumes are questioned now. So it is not possible to have long duration plume at the same place. So probably there is a multiple plumes that coming different times. Just like that, we have a short duration, a large igneous provinces. So it may be 5 to 10 million years or something, yeah, and or up to the 50 probably, up to the 50, not more than 50 million years. Yeah.
It's much more than 50.
Yeah, could be. So that's a big question. Yeah.
I have just another query here. From the northeastern part of the country, there are reports of mafic dike swarms and also carbonatites which are related to Kerguelen type of
Yeah.
plume.
Yeah.
But at the same time, there are ophiolites where the oceanic crust is also formed at the same time frame. So how you can think of that the plume head as well as new oceanic crust formation, they are of different composition, how they can in a geodynamic setting can be seeded. Have you understood my
Yeah.
query?
Many times that plume indirectly involved in magmatism. Only heat can that help to melt that is there, but not directly. So
Okay, so
if you have a same age or something, so there may be some plume has given the heat to melt the. Yeah.
Just to answer Saibol's question, all the dikes are channelized by deep-seated fractures and faults. So their orientation is controlled more by them than by the plume head. Maybe it is a melting source, but the orientation is controlled by pre-existing. Right.
Okay, thank you everyone for questions. Thank you, Professor Rajesh. Please do interact with speakers, different speakers at the end of the session. Thank you, Professor. Now I request Professor Sukanta Dey to come and give his presentation on crustal growth and reworking in Western Dharwar Craton.
I will go there. I'm a teacher. Where is the pointer? Yeah. So from the Venus, let us come back to the Earth. So one of the most significant changes that Earth has ever witnessed, that is the formation of continental crust. Okay, so we know that initially it was mostly mafic ultramafic crust, but slowly with Earth's lot of processes, continental crust started forming. So that has fundamentally changed many features within the Earth. So these are some of the research questions that our group is trying to answer. That yeah. So how much in the past we can trace back the continental crust formation, and then what was the crustal growth, whether it was continuous or it was episodic. If it was episodic, then what was the geodynamic significance of all those events? Then is there any temporal change in the pattern of crustal growth? And of course, the nature of source mantle. Okay, so when continental crust is derived from mantle, so mantle gets depleted in incompatible trace elements. So when was that depletion started significantly? So there was a lot of controversies regarding that. Some people suggest that it is only about 3.2 billion years ago that significant depletion started. Before that, it's mostly chondritic mantle. But some other evidences like Jharkhand hafnium isotope, etc., people suggested that even within the Archean there was mantle depletion. So all those very fundamental geological questions, the broad geological questions. So why they are difficult to answer? Because if you talk about the early period of the Earth history, from Archean to Paleoarchean, Mesoarchean, we have little crust left. So how to answer or how to address these problems? So if we want to answer this problem, one way is that we may go back. Probably there is some barrier like this. Yeah. So maybe we can study the Cratons which preserved significant amount of older crust, Paleoarchean, Mesoarchean crust, which stabilized early. Just like one of them is the Western Dharwar Craton. If you see the Western Dharwar Craton, the basement, that the boulder rocks are this Granitoid gneisses and this blue color, this linear narrow fish belts, the Sargur group, they are very old. So we can go back to them. And over this Paleoarchean, Mesoarchean basement, another generation of volcanosedimentary rocks formed. these are actually hosted by this Dharwar supergroup of rocks, around 2.9 to 2.55 billion years old. The sediments which are now preserved within these volcanosedimentary basins, they are actually derived from erosion of a continental platform. Continents which are probably existed in their source areas, which may not be existing now, but their signatures are preserved within these sedimentary rocks. So when this volcanosedimentary rocks started, then it was a stable continental setting. We know that because it was a very mature quartz-granite, quartz-pebble conglomerates. So the advantage of this so if we talk about the sedimentary archive, why it is advantageous? Because it represents the vanished, which is eroded continental crust, and the rock composition can be linked with the tectonics and composition of the source. And of course, detrital zircons are very advantageous because they can see through the crust formation events, and their composition, their age can be related to geodynamic processes. So with these objectives, we have studied two greenstone belts, sedimentary rocks, which are occurring at the basal part of the two greenstone belts. One is this Baba Budan greenstone belt, and another one is the very thin, this is a Sigegudda greenstone belt in the western Dharawar Craton. So this is the Baba Budan greenstone belt. So we have collected sandstone samples from the southern margin. This is a group of quartzites and quartz-adenites, very mature sandstones, quartz sandstones, and these are some of the field photographs. We can see most of the pebbles are quartzite and quartz, and here that grand unconformity between the weathered Paleoarchean, Mesoarchean granite and overlying these quartz-adenites and quartz-pebble conglomerates. We have carried out some of the lithologging as well as paleocurrent analysis in order to understand from which portion these sediments were received. Then here we can see the thin section photographs. Most of them are very quartz rich. This is very important. This is very useful for detrital zircon studies because all these formed over a stable continent. So we expect that they have received sediments from a wide, large area. So, and this is the Sigegudda greenstone belt. Here along the western margin, we can see these are the white portion is the basement granitoids, over which this quartz pebble conglomerates and quartzites. This band here we have collected the samples. These are some of the field photographs, and they are also quartz rich, quartz pebble conglomerate. So these are the CL images, cathodoluminescence images of the detrital zircons. We can see the concentric joinings, mostly they are magmatic, and these are the spots of UPB analysis, age analysis, and the larger spots are hafnium isotope analysis. And here is the zircon trace element plot. This trace element ratio is indicative of tectonic setting. This has been these fields have been already published. So we see that most of these zircons were derived from continental granitoid sources, and these three samples analyzed for UPB. So we can see that, and here on the right hand side we have plotted only those zircons whose concordance is more than 95%, and see that the majority of the zircons falls within this group, 3.4 to 3.1, whereas there are some other zircons like 3.5, 3.6. Presently we don't have crust rocks exposed of that age in the western Dharawar Craton. And if you see that the age pattern combined with our analysis, our data, with the all literature data, it is very important. We can see that the major event of crust formation within the western Dharawar Craton that happened within this time period, 3.4 to 3.2, But there are some younger events also, 3.1, etc. This is the time period around 3.1. We get intrusion of the first potash-rich granite within the Western Ghar Craton. That marks the stabilization of the Western Ghar Craton. But there are older ages, 3.6, 3.5, etc. And there are different peaks. The major peak is around 3.2 billion years ago. So that is the most significant event of crust formation within the Western Ghar Craton. And this is the Jharkhand age versus epsilon hafnium value. So if the Jharkhand's analysis, they plot above this 0 line, that means the magma is derived from a juvenile source. That means it was a short crustal residence time. The magma was derived either from mantle or a juvenile source. The juvenile source was derived from a depleted mantle. And if the samples plot here, that means it was derived from a rock which is formed by reworking of older crust. So we can see two or three major events. One is that the older Jharkhands, 3.6 to 3.7 billion years, they fall on a line which you can trace back to mantle up to 4 billion years. That suggests cryptic evidence that the crust formation within the Western Ghar Craton started possibly by early Eoarchean or Hadean time. Then there is another one which started from juvenile crust, positive values, which started from around 3.5 billion years ago, and it goes up to this, around 3.3 or 3.35. So we interpret this term or this pattern as initial juvenile crust formation and the reworking of the juvenile crust up to here. And there is another event. This is the most significant event of crust formation within the Dhara Craton. It started with addition of juvenile crust in the craton and its reworking up to this. And here, this marks the significant event of reworking of older crust at around 3.1 billion years ago. So this is the So the Jharkhand trace element, detrital Jharkhand trace element also gives a lot of information regarding the variation of crustal thickness. So here we can see, for example, this is an indicator of crustal thickness. So if it has more U by YB ratio, that means the magma is derived from reworking at higher pressure. Why? Because ytterbium is taken by garnet. If the crustal melting takes place at great depth, it stabilizes garnet in the residue. So in the magma, this becomes higher. So I'm just explaining one of the diagrams. If we see that with age, we are getting much higher and higher uranium by ytterbium ratio at this point of time. So around 3.2 billion years ago, the crust, continental crust within the Western Dhara Craton attained the maximum thickness. And also you can see the much spread of this U by YB ratio. That means that crustal melting was happening at different depths. So, and then again there is a reduction of that top envelope. So probably there was a reduction of crustal thickness at this after 3.2 billion years. So now I summarize how to connect this with the tectonic setting, in which tectonic setting the crust, continental crust formed within the Western Dhara Craton during Paleo and Mesoarchean time. So if we see the rock association within the different greenstone belts, in the Sargur greenstone belt, etc., we don't get rocks typical of subduction zones, just like we don't get andesites, we don't get niobium enriched basalts, arachites, etc., etc. So rather, we think that it was a mantle plume related tectonic setting. The initiation of the continental crust started probably within a oceanic plateau environment. Then there was repeated mantle plume derived magma underplating and interplating that actually triggered crustal melting and formation of the continental crust. So this is in this type of setting we get dome and keel-like structure. So if you see these two type of greenstone belts, so if you see, we can see this is one Hwele-Narsipur greenstone belt. This is the greenstone belt rocks, and these are the granitoids, white and pink ones. And if you see the cross sections, we can see the greenstone belts are sinking and the granitoids are doming upwards. So that's why if we go to at the center of the granitoid domes, we get flat foliation pattern. But if you go to the margin of the granitoids at the adjacent to the greenstone belts, we get very steep foliation patterns. So our last conclusion is that within the Western Dhara Craton, it was the crust actually probably formed in episodic continental crust formation events, and it was probably related to episodic mantle plume related or mantle upwelling related magmatic underplating, and episodic reworking of the continental crust and formation of these granitoid greenstone belts. And this was published in Lithos, the work. Thanks for your attention.
Thank you, Dr. Day. Exciting topic. We can have one question, just one question, please.
Sir, you mentioned the crust formation process, the major crust formation process in the WDC is 3.2 GA. Means crust attended its maximum thickness during this time. So in Dharwar Craton, the oldest dike swarm is 2.37. What's your perspective of getting oldest dike swarms of the Indian silt in the WDC? Because oldest dike swarm currently in Indian silt is 2.8 in the Singhbhum Craton. So can we expect some oldest dike in WDC?
Why not? But you know that formation of dikes and all those things, okay, this is a big question. We don't, why in Singhbhum Craton the crust formed around 3.3, but we don't get that much old dikes. So probably, formation of dike requires some kind of fracturing and all those things. Okay, so probably crust was not that rigid. So I am not expecting of that old dikes. Okay, you require for dike, it requires fracturing and all those things, so the magma can come up along some conduits. So I'm not expecting that, at least not at 3.2.
Sir, there is one quick question. Nice presentation. We have a report of 3.2 to 3.3 GS zircons in a kimberlites which erupted in the eastern Dharwar Craton. What could be your explanation for this?
It's possible because of the genocrest. In eastern Dharwar Craton, there are, what I believe that there are microcontinents which are older. Eastern Dharwar Craton is mostly 2.7 to 2.5. So why you are getting? Because probably there are some microcontinents which are much older. So probably your kimberlites also have acquired the zircon genocrest from those older crusts. May not be. Because there are 3.1 reported edges from the granite edges from the eastern Dharwar Craton.
Okay, kindly discuss this afterwards because we are a little bit behind. Thank you, Professor Day. I now request Dr. Simontini Sanserma to come and give a presentation on petrology of Bhuj and Malwa volcanics from Deccan. Yeah, of course.
Is it okay?
Otherwise, they are the losers because of the previous.
I cannot hear it. Okay. This is the pointer, no? Okay, so again coming back to the LIPs, that is the most well-known and one of the largest Deccan volcanic province. So here we have tried to understand comparative petrological evolution of the Bhuj or Kutch volcanics as well as the Malwa volcanics, which forms the happening? Okay. Which forms the northernmost extension of the main Deccan trap volcanism. So as you can see that Deccan volcanic province has this huge areal extent of around 5 lakh square kilometer, and mostly they are centered in the central and western Deccan. The main voluminous activity is found in this area, which is around 65 million years ago. But prior to that, actually, the Deccan volcanic activity has initiated in this Kutch region, which is dated to about 68 million years by various geochronological data. And in the Malwa region also, there is a huge extent of volcanic traps are found, which are beautiful, these tabletop mountains, just like found in the Western Ghat regions. And it also has a very huge areal extent of about 80,000 square kilometer. So the main pulse is in this area is thought to be due to the mainly upwelling of the plume head. However, the I don't know, something is happening, it's not coming. Okay. Yeah, it came. But the volcanic rocks which are found in these Kutch regions, they are very alkaline and diverse in nature. And it has been, by various method, it has been found that the main reason of this alkaline and diverse nature is probably due to the mixing of the subcontinental lithospheric mantle in this region. Because in this region, there has been prominent graben systems are observed, which is one of the graben system is in this Narmada Tapti Valley, one in the Kambe Basin and one in the offshore region. And because of this continental rifting and the magma which has been generated because of that, and the mixing of this plume head also, this region has much more diverse and very interesting assemblages than the main Deccan trap, which is quite consistently tholeitic in nature. So I'm directly going to the study area. So I have actually interchangeably used this Bhuj volcanics and Kutch volcanics. So I apologize for that. But this is the main exposures are found in the Kutch region in terms of these volcanic domes and plugs and intrusive bodies. So these are the few locations where we have seen massive to vesicular basalts, and in one particular location we have seen this beautiful transition from massive to vesicular one. And so total 8 locations we have visited, and in one of the location 6, we have got a very felsic rock, very fine grade felsic rock, and we think it's a rhyolite. So, and if you can understand here that there is a beautiful gradation seen from the lower part, which is much coarser, and towards the upper section it is finer. So, and coming to the Malwa Plateau, main Malwa Plateau region. So, contrastingly, the topography of the Malwa region is very distinct in the sense it is same as the western and central Deccan with these tabletop mountains and very beautiful columnar basalt where we all have posed here. So I'm kind of camouflaging here with the greenish alteration found in the columnar basalts. And not only here, we have seen these greenish kind of alteration patches, just not as green bowls and red bowls in between the different lava flows, but all over the columns. And here also we have found, in many places we have found these columnar basalts. And other than that, massive vesicular structures, flow textures, spheroidal weathering, these are also observed in the field association. Coming to the petrography, I don't know, am I not? Where should I point? Here, no? So coming to the petrography, these are the some photomicrographs from the Kutch region, where we have seen this olivine, big olivine xenocryst even in hand specimens. And other than, this is one of those xenocrysts which is almost 3.6 millimeter under 4x. And other than that also, big olivine and pyroxene phenocrysts are present here. Some have plagioclase, but mostly these are olivine-rich varieties. But the ground mass is very fine-grained, and ground mass is mainly composed of plagioclase microcryst, pyroxenes, titanomagnetite, as well as snephylines. In contrast, the Malva basalts do not have as such olivines or pyroxene in the phenocryst population. Rather, they have large pyroxene, lathe-shaped phenocryst. In one sample, we have seen this clustering of plagioclase phenocrysts like glomeruloporphyritic textures. In only 1 or 2 samples, we have found olivines and pyroxenes, but they are very highly fractured. And in one of the area, we have found this megacryst, the giant plagioclase basalt, where we have seen this beautiful zoning also. So we have tried to do the crystal size distribution from which we can comment on the growth history of the different grain sizes. So the idea is that if the grain sizes are smaller, like in the case of ground mass, it will plot towards the origin and will have much steeper slope, indicating much higher growth rate. Whereas the ones which are like the phenocrysts, having higher grain sizes, will plot away from the origin and have much gentler slope, indicating slower growth rate. And if we extend the this thing also, the y-intercept, then it will give the nucleation density also, which I have not shown here. But in most of the samples, we have seen that at least 2 stages of ground mass population has been seen. One is from 0.1 to around 0.27 millimeter, and one is from 0.27 to around 0.35 millimeter. So only from 2 places in Bhuj, we have done so far the mineral chemistry, and mostly the ground mass pyroxenes are diapsetic in nature, with only one falling in the augite, and one a bit larger phenocryst is falling in this pidgeonite phase in location 1 of Bhuj. Whereas coming to the feldspar compositions, so in location 1, feldspar composition is more or less very consistent in the labradorite domain, whereas only 1 or 2 falling in the anorthoclase and andesine. But in location 2, the feldspar composition is quite varied, from very potassic, anorthoclase to very albitic to up to labradorite it was found. And Ng hash values of the olivine xenocryst towards its core is 84 to 86, whereas towards the rim it decreases up to 76 to 78. While the phenocrystal olivine and the clinopyroxenes, they are showing an Mg hash value of 68 to 80, which suggests again that there is a definite compositional variation in this larger olivine xenocryst, which we can see in the hand specimen also, and the smaller ones, indicating a dynamic crystallization under disequilibrium condition. So we have done some trace element analysis also, bulk rock trace element, and this is the chondrite normalized trace element RDD pattern of the Bhuj volcanics and the rhyolite, where it can be seen the all are quite LRD enriched light rare element, whereas the Bhuj volcanics in general has a positive europium anomaly, while the rhyolite one has a negative, and the same is seen in the Malva basalts. So although they have plagioclase phenocrysts, but they are showing a negative europium anomaly. Now this particular sample is the one which only has this olivine and pyroxene phenocryst, and they have very less plagioclase phenocryst. Ground mass they have, but not as much as the other one. And this particular L15, L17 are the ones where we have found this giant plagioclase megacryst and the big phenocrysts. So probably that's why it has a lesser pronounced negative European anomaly. And primitive mantle normalized trace element pattern shows that all are again quite high in tantalum, somewhat niobium also. But in case of Bhuj, there is not as much zirconium hafnium enrichment as it can be seen in the rhyolite, as well as some of these Malva basalts. And here yttrium positive anomaly is not also pronounced in the Bhuj volcanics, but it is pronounced in the rhyolite sample as well as most of the Malva basalts. So this is a comparative distribution I have given for the trace elements of the average Bhuj volcanics, Malva basalts and the rhyolite sample. And as you can see from here that the Bhuj volcanics are very extremely enriched in strontium, exceeding 1% also at some times. And also they have very high concentrations of chromium, nickel, barium and RED. And on the other hand, the Malva basalts have higher concentration of scandium, vanadium, and to some extent copper and zinc. Whereas rhyolite has overall lower concentration in most of the trace elements except for strontium, zirconium and barium, as well as have comparatively much higher concentration of lead, while rest of all the samples have less than 4 ppm. So coming to the initial findings, so the presence of olivine xenochrist likely represents the subcontinental lithospheric mantle beneath this area which ascended during the eruption, and the smaller phenocryst suggests that it is probably during the later stage of magma crystallization and cooling. And the diverse compositions of the feldspars and higher Mg hash values of the olivine xenochrist force compared to its rim and the phenocrystal phase indicates again a dynamic setting of magma generation, which probably due to disequilibrium crystallization and melt fluctuation. That is also observed in the sector zoning of the pyroxenes of the same area. And Malva basalts, their textural and mineralogical composition as well as the trace element composition also vary from district to district within a very short distance even. And the zoning in the plagioclase megacrest is also due to a very rapid change during ascent. So that can also, and probably this is a xenochrist, so it can shed some light in the contribution of SCLM in this area. And at least 2 stages of nucleation was identified in the groundmass plagioclase, probably due to staging period of magma. And the presence of olivine xenochrist in the Bhuj volcanics and their complete absence in the Malva basalts suggests that probably the Bhuj volcanics are derived from a much deeper part of the mantle than the later. So these are the future works which are pending, that is the major oxide analysis and mineral chemistry of some more samples from both the areas. And this work is actually part of the
we'll read it.
Thesis.
We can read it. Thank you.
So I will like to end with this beautiful pile of columnar basalts. So thank you everyone.
Thank you, Dr. Sen Sharma. This topic is very dear to me personally. 1 or 2 questions again, hopefully from youngsters.
Sir, this is from the Devas area, nearby Devas area. Yeah.
Simantini, to my knowledge, a lot of earlier workers have suggested Malva traps have flowed from west towards east. Have you found any eruption centers in the field work, or what do you think about this status?
Sir, as such, we have not found in the field, because one of the problem which we encountered this time when we went there is very much destruction due to the rampant construction in those areas. So wherever we could find some exposures, we sampled from there. But a very planned way to do to get this kind of information was not possible because there were so many places which has been totally flattened down, and other places are within the reserve forest areas.
Shivantini, I have a general I have a query. If your flow contains too much of xenocrest, then what was your analytical strategy to know the bulk rock analysis?
So bulk rock analysis.
Did you exclude the xenocrest during
Yeah, so xenocrest we have few samples we have done. I plan to do some more, but other than also the ground mass composition, for that also I wanted to do the bulk chemistry also. The both is we plan to do, the xenocrest also and the bulk chemistry.
Okay, one last question from Ashish. Sorry about this, but
what you worked on, like in Bhuj area, these are the intrusions and plugs of the igneous intrusions.
Yeah.
And in Malwa, they are flows.
They are flows.
So that's why you have xenocrest here and
Yes,
you don't have xenocrest
because
there.
flow texture is not as such present in those Kutch regions. So mostly
There are a few flows.
very
so it's
few.
better to compare.
Yeah, very few.
Just a
but-
comment.
Yeah, very few.
I just wanted to know that I see your trace element chemistry that you have shown. Why all the rhyolites, or you have only one rhyolite probably,
Yeah.
which has lower concentration of the rare earth compared to the basalt. Just think over it.
Yes.
And why some of your data shows positive yttrium anomaly, okay, compared to others. If you see the rare earth, you don't have that.
Yes.
So whether it has anything to do with the analytical problem or it is telling something, just think over.
Sir,
I'm not
I
telling-
don't think it has analytical problem because it is consistent in all of those. But so the Bhuj volcanics doesn't show yttrium positive anomaly. That is shown in the Malwa basalts. So my So one of the thing is that I have only so far able to do the trace elements. So with that I have to insert some of the major elements also to get the whole picture. So probably because of that there is some variation showing. So once I am able to do the major element and plot all the elements which should be there in that primitive mantle normalized trace element pattern, then maybe I will get a bit different picture. So I'm
Okay.
just waiting for that. Yeah.
okay, thank you, Dr. Sen Sarma. Okay, the last talk of the session is by Dr. Indrajit Saket. I request him to come and give his presentation. Granitoids from CITZ.
আইআইটি ভুবনেশ্বরে আছি এখন আমি পাশ করেছি প্রেসিডেন্সি 2012 ব্যাচ পিএইচডি এনআইও গোয়া অভিষেকের কাছে না
What is the up down? Next. So, good afternoon. So my title of the paper, Geochemistry, Geochemical Characterization and Petrogenetic Studies of the Granitoids of the eastern part of the Central Indian tectonic zone. So these are the outline. First objectives of the study, petrography and determine the mineralogical composition and their relationship, and also to determine recognize the mineral chemical evolutionary path and nature of the parental melts, and estimate the pressure temperature of the granitoids during the melting evolution. Also understand the geochemical characterization of the granitoids to understand the felsic magmatism, petrogenesis, and Precambrian crustal erosion of the central Indian shields, which are associated in these granitoids in the eastern part of central India, Anuppur, Pendra, and Umaria granitoids. And also know the magmatic crystallization and emplacement is to understand the source and tectonic setting of the granitoids. Now, also we have elaborated and existing geodynamic model for the responsible for the evolution of the granitoids in the CITZ based on geochemistry data sets. So now these are the introduction related to continental crustal evolution. The Earth continental crust represents the oldest rock records on the formation and growth of the continental crust evolved through the different geologic times. So now these are the Precambrian time periods represent the largest part of the Earth geological history from Archean to Proterozoic eons. They have also various workers have been done Precambrian terrains widely distributed in all over the world. Initially known as Greenland, McLennan et al. 1984, India by Radhakrishnan 1983, Naqvi and Rogers, Montana and Wyoming's Muller et al. 1982, and Australia and Limpopo, Wales, South Africa, Taylor et al. 1986. So now these are the introduction part of the granitoids. Granitoids, that is the consist of the most important rock type for the formation of the continental crust, and these are the formation of the granitoids that can say the formed by the partial melting of the crustal components in the lower to middle crust, differentiation and evolution of the mantle derived melts, and we can so know the variable degree of the interaction. So why need the granitoids for study? First is that most voluminous constitute of the continental crust, to consider the heat and float sources for the important mineralization, and quartzo-feldspathic, hardly recyclable. So also controlled by the physical and chemical conditions of the sources, amount of the residual minerals, varying anatectic conditions, and stage of the magmatic differentiation and tectonic settings. So now these are the regional geological map of the central tectonic zones. The central tectonic zone, northeast to southwest trending, they have demarcated by the two cratonic blocks, northern margin of the Bundelkhand Craton and southern margin of the Bastar Cratons. So now these are the central tectonic zone. The study area belongs to the southern margin of the Mahakaushal belts, which is commonly separated by the Son-Narmada South faults and commonly associated with also the Gavilgarh-Tansiyar zone. Now you can see this is the cross section of the CITZ, and also three supracrustal belts in the CITZ, and three granulite belts commonly runs through the CITZ. So these are the some various workers have been done, including Mahakaushal, Betul, Tansiyar in the CITZs. So recently, the Yadav et al. Madan Mahal and Sidhi granitoids have been geochemically, these are the trace and rare earth elements geochemistry by the INDIST, and except europium anomalies, and they have also indicating some A2 type affinity and post-ecological extensional environments. So now these are the previous geochemical studies in the Mahakaushal belts, intrusive granitoids done by the Pandey et al. Jirgadandi, and also studied some calc-alkaline nature, and RVSR 1813 plus minus 13 MA and 1860 plus minus 180 MA. So pink and grey granitic rocks from the Madan Mahal granites, this is done by the Yadav et al. 2020. These are the studied granitoids. They have discussed the Columbian supercontinental assembly. So now these are the saucer group of the geochronological studies. So this is my study area. The study area mostly covered by the Gondwana sedimentary rocks. These are the granitoid rocks, which are mostly in the Anuppur granitoids and Umaria, and those are the some Pantra granitoids. So now these are the field observation. The study area mostly classified based on the field observation, three groups, and petrographic characteristic. Field observation mostly pink and grey granitic rocks, and petrographically those granitic rocks are mostly consist of the quartz, K feldspar, plagio-clays, and biotite as essential minerals. However, some accessory minerals such as the hornblende, apatite, and some zircon as accessory minerals. So this is the pink granite, mostly some coarse to medium grain with porphyritic in texture, and also found some microgranule enclaves. Microgranule enclaves also we can say the magmatic magma mixing and magma mingling processes. Another is the pentagranitoids. Those are the also pink and grey granitic rocks, and some also found some K feldspar and plagio-clays. These are the sericitized due to hydrothermal alteration products. And another is the Umaria granitoids. These are the weakly deformed granitoids, and those are the pink granitic rocks and grey granitic gneisses. And essentially those, and some these are the E and F photograph also, some also indicating some quartz deformation. So these are the mineral chemistry data set, K feldspar and plagio-clays. Mostly K feldspar mostly belongs to the Canadian field. However, the plagio-clays in the L/2 Andesine affinity. And biotite mostly consists of the in the granitoids, also indicating the primary magmatic nature of the granitoids, and they are also indicating some crustal sources. And siderophylitic in nature. And the titanium in biotite thermobarometry also indicating the temperature range between 716 to 30 degrees Celsius, and pressure between 4.24 to 5.55 to 5. They can say the initial derivation of the magma through melting the plate interiors. So the geochemistry data set also indicating some Harker variation diagram, negative correlation also indicating some fractional crystallization process such as the hornblende, plagio-clays, K feldspar fractionation, and positive anomalies also some correlation also indicating some elemental mobility. So now these are the normative classification of the granitoids. Most of the granitoids belongs to the granitic in nature, and some also belongs to granite to granodioritic. So these are the magma classification plots. They have also indicating some calc-alkaline nature, and calcic to alkalic, and calc-alkaline to sosonitic series, and magnesium to ferron in composition with metaluminous to paraluminous composition. So now these are the trace element geochemistry. This is the trace and rare earth element geochemistry diagram. This is the chondritic normalized rare earth element patterns. Most of the light rare earth elements are enriched and flat HRE pattern, and europium is the negative anomalies which are indicating plagio-clays accumulation. Another is the pentagranitoids, that is the also based on classified based on the abundance chondritic times, and pentra also they have classified two natures. First is the negative anomalies also indicating plagio-clays accumulation, and some curving in nature we can say also the residue in the source of the plagio-clays. So another is the chondrite diagrams in the Umaria granitoids, negative correlation in the plagio-clays, and some they have classified two category, and plagio-clays accumulation is the positive anomalies. Okay. We have compared our geochemical data set from the Mahakaushal granitoids. Most of the granitoids that is the belongs to the Paleoproterozoic ages. Another is we have compared our geochemical data from the early and late Archean Proterozoic and Phanerozoic and the Mahakaushal granitoids. those are the similar sources and characteristics. However, spandra granitoids, those are the some different source. So these are the high aluminum TTG and low aluminum TTG data set from the Condi et al. So these are the most of the granitoids belongs to the low aluminum TTG. However, the spandra granitoids mostly belongs to the high aluminum TTG rocks. So these are the fractional crystallization and partial melting of the curve. Most of the granitoids that is belongs to the fractional crystallization, and some of the samples also indicating the partial melting nature. Geochemical data compared with the Archean granitoids, most of the granitoids that could be belongs to the post-Archean granitoid fields. And also this is the post-Archean granitoid fields of the granitoids. So nature of the magma, that is the most of the granitoids that is belongs to the A-type granites, and however some granitoids that is the I and S-type in nature. In the tectonic setting, most of the granitoids that is the A1 to A2 type affinity, and also indicating the inaugurogenic setting with post-collisional tectonic settings. We have compared our geochemical data set from the Mahakoshal, so we have following for the some elaborated model from the Roy and Prasad and Vani Mandal in 2016 and Roy et al. 2020. So now the mineralogical assemblage and the textural feature of the magmatic rocks can be indicate the nature of the protolith. Perthite and meromictic texture, intergrowth texture can be common in the rocks, which can also indicating the magmatic origin. Also observed some microgranule mafic enclaves in some places, suggest the magma mingling of mafic to hybrid magmas.
Can we just leave it here? We can read and can ask, because we can have a couple of questions.
So we have future planning for the SMND isotopic data to delineate the source of the igneous melt, and we also planning for the uranium-lead zircon dating for the order of the magmatic crystallization age. Thank you.
Okay. Thank you, Dr. Saket. We have time for one or two questions. Quick.
Saket, very nice characterization of these rocks. So any idea about the age of emplacement of these granitoid rocks?
We have compared our geochemical data from the Yadav et al. 2020.
You do not have uranium?
I have no geochemical data. I have future planning for the analysis. But we have also elaborated these data from the Mahakoshal, so we can also follow some paleoproterozoic. These are the ages.
And what will be the possible protolith source rock whose melting has given rise to this? Is it continental crust or mantle melting?
Some mental melting is a possibility.
Mantle melting,
yes.
Considered.
Okay. Anyone else?
Nice talk. So I saw in one of your diagrams you had a strong negative europium anomaly, and at the same time there are samples which do not have them, very flat, no europium anomaly. So how do you reconcile them together?
Due to the some crustal sources region.
Sorry, crustal?
Crustal sources.
Okay.
Fractional crystallization.
We have a question from Jyoti Shankarda.
Hello. Saket, this is very nice presentation. I have just one small inquiry. You have shown as field photographs good exposures of porphyritic granite. Am I right? So do you have any idea how those porphyritic granites form, whether their generation is somewhat different from your other granites? I just want to know, do you have gathered any idea regarding that?
Again, repeat these questions.
How do porphyritic granites form? That is the question.
Okay.
Quickly, a quick answer if you can.
We cannot.
Or maybe you can discuss with him.
I will discuss it.
Okay. Thank you, Dr. Saket. So this is the end of this first session. I thank all the speakers and the audience for your participation. The next session will be chaired by Professor Rajesh Srivastava and Dr. Ram Mohan. So over to Rajesh ji.
And now I will request Talat Ahmed sir to give a memento to Hatu sir. So please.
I think we have to start the next session. So myself and Dr. Ram Mohan will chair this session. And first talk, there are 4 talks. So first talk is by Professor Mandal. So please. You have 20 minutes, so after 70 minutes I will just...
Which one? The slide movement? Forward? So I will be talking about the complexities of the banded gneissic complex. Okay, the term banded gneissic complex has been used, and there are many other terms have also been used, but I will stick to the term banded gneissic complex as it is a formal, non-racked lithodemic unit, and this term BGC, banded gneissic complex, it nearly fulfills the recent international stratigraphic codes. So compared to other terms, so we will go on sticking to this term, banded gneissic complex. This banded gneissic complex is the gneissic rock, that basement gneissic rock of the Aravalli Craton. The whole banded gneissic complex is these parts, this part as well as this part. They can be, they have been called as banded gneissic complex, but they can be conveniently divided into 2 domains based on their temporal evolution, their metamorphic grades, and also lithology. Both these terrains, both these 2 domains, they have similar lithologies. The gneisses, grey gneisses, they have also metasedimentary rocks and also metabasaltic rocks. Mainly I would be talking mainly about the gneissic part of both these 2 terrains, 1 and 2, BGC1 and BGC2, and also the basaltic rocks, mafic rocks of both these 2 terrains. I will not include sedimentary rocks in this talk because of time. This terrain, south of Nathdwara, this is typically called banded gneissic complex 1. This is undoubtedly Archean in age, and which is unaffected by the Proterozoic 1.7 tectonothermal events, whereas this part, this terrain, BGC2 terrain, is definitely affected by Proterozoic 1.7 tectonothermal event. Interesting part is, based on our chemistry, we can show that the modelage of this terrain and this terrain, geochemical neodymium modelage of these 2 terrains are same. This will indicate that once they were formed at the same time, these 2 terrains were once upon.
Here, this one is pointer.
Okay.
This one.
This one. Okay. These 2 terrains were once upon a time, they are formed by the same process. first I will take the gneissic rocks of BGC1 terrain, this one terrain. These are the grey gneisses mainly. Earlier, previous workers, they have considered all the gneissic rock to be TTG without assigning geochemical connotations. But our work on geochemistry, we have shown that all gneissic rocks are not TTG rock, but majority of them are TTG rocks. About 75% are TTG rocks, TTG gneisses. But there are some other potassic gneissic also, about 25%. And their detailed chemistry indicates that these gneissic rocks are derived from enriched sources. You see neodymium positive and many other isotopic, many other characteristics. So the enriched source for these gneissic rocks, and melting was at variable. Melting, these are the TTG gneissic rocks. We can see it indicates variation in depth, pressure. Okay, and also there are subduction signatures in these gneissic rocks. So we are trying to find out, can we get any geological signature for these things? So luckily we got that the gneissic rocks, they contain some mafic enclaves. Now when we did chemistry of these rocks, their chemistry is enriched chemistry, and they show a enriched YB type, oceanic plateau type chemistry. So the enriched nature of the gneisses, they clearly indicate a normal mafic crust cannot be a source, but enriched source, mafic source can be the source. So we thought that probably the melting of such mafic rocks, enriched YB type mafic rocks, gave rise to these gneisses, and these are remaining unmelted part of those things. So it is proposed that such enriched mafic rocks probably gave rise to the gneisses, and these enclaves represent the undigested part of these rocks. And the TTG rocks have been generated from partial melting of such rocks there. For the transitional TTG, which are potassic in nature, they show heterogeneous and enriched characteristics, but they show shallow depth of formation. So we say that this transitional TTG, they have formed from the partial melting of such TTG rocks. So those TTG rocks, they again melted, reworked to give rise to these potassic gneissic rocks. So what we propose that oceanic, normal oceanic, not the normal oceanic crust, but enriched oceanic crust, ocean plateau, probably got melted in a subduction zone area. But this is a difficult proposition. It is not possible to melt, to subduct this thick oceanic plateau. This is the only problem with this model. But we have some examples of oceanic plateau being subducted even in modern days also. So probably such things happened, and at different depth it melted, and they gave rise to different geochemical signatures of the TTG gneisses. And so we say that this whole BGC terrain, they were formed by this same process. Later, it was divided into two with the formation of Aravalli volcanics. And the work of Professor Talat Ahmed and his group, they also say that this was an opening of the basin. So we can now say that BGC1 and BGC2 is now detached with the formation of these things. Then we talk about basaltic rock. Now these mafic rocks are confined only in this part, in a linear belt. These are the gneisses and granites, but the mafic rocks are exposed only in this part. There are many gneissic rocks, many mafic rocks, and in literature, all of them have been clubbed to be amphibolites. But here we make distinctions. These are the mafic enclaves, which are distinctly older. There are some mafic dikes, which are again younger. We have included only the mafic, this metabasaltic rocks. These are the metabasaltic rocks, which are mainly found in the Rockwell, Sangwa Rockwell section, and these are very peculiar rock association. These are intercalated mafic and felsic bands. These rocks are not very common in Archean crust, in Archean terrains. These are very peculiar rock association, and they indicate a kind of a spreading kind of scenario where such types of intercalation of mafic and felsic can be seen. So based on the geochemical characteristics, we have categorized these basaltic rocks into three groups: arcthuliite basalt, boninites, high magnesium andesites, and niobium enriched basalts. These rocks, mafic rocks, are not well dated, but they can be clubbed, bracketed in this bracket 2.7 to 2.6. So they are all thuliites and basalt to basaltic andesites. As I said, based on their chemistry, we have these things. Okay, about the source of these basalts, when we try to understand the source of these basalts, then we see that the source of these basalts were metasomatized by fluid mobile elements, and they have some subduction signatures. So we say that these basalts were formed from a metasomatized mantle in a subduction zone settings. Now, since these boninites, high magnesium andesites, and niobium enriched basalts are exclusively found in the subduction setting, so we are compelled to believe that these mafic rocks were formed in a subduction zone setting. So these were the gneissic terrain already formed with the enclaves, and this part in a supra-subduction zone kind of thing, this underwent a stretching and a small linear basin was formed. This is the Sangwa Rockwell section, where we have all these things in the initial part, boninites and all those things will happen. In addition, we will have two kinds of sediments. One kind of sediments, immature sediments, would be derived from the Craton areas, which are now occurring as these immature sediments, mainly mafic schist. This is mica schist. And also, we found these basalts are associated with chert. This has been in literature reported as quartzite, but our detailed studies have shown that instead of quartzite, they could be better called as metamorphosed bedded chert, and they are associated with this thing. So with this way, we can explain the linear occurrence of the basalts as well as the sediments along with the chert. So these are the things that I have already explained. Now there are some undeformed granitoids, which are mainly not dominantly gneissic fabric. These are Berach, Untala, Aha River, and many other rocks, many other small protons, and they are mainly bracketed. They are generally clustered around 2.5 billion years. They have distinct different geochemical signatures, and their geochemical signatures we have explained mainly in terms of change in the source. The Untala Gingla, they mostly show TTG type of signatures where we say that it is the mafic crust itself undergoing melting and giving rise to this TTG suite. Through time, the source shifted from this mafic crust to the mantle wedge. So mantle wedge started melting and provided inputs, and these mantle inputs, they introduced to this sanuquitoid of kind of signatures, and these are shown in the barrage granites. And in the some other parts, they are mainly crustal melts, and these rocks are found in all the places. So we say that these gneisses, which are mainly 3.3 to 2.7, and also these granites 2.5. So the age of this whole terrain would be this. But later, when the Aravalli would be closed, this part would be remobilized, and at some time, maybe around 1.7. But they will carry the geochemical many signatures, which are very common to these signatures, including geochemical signatures. As I said, the model age of these things are actually same with the crystallization age of this terrain. Now we take the basement gneisses, the gneissic rock of this part, BGC2. We conclude that based on their chemistry, there are two types of gneisses in this part. One has a very strong similarity, sodic gneisses, which are very strong similarity with the gneisses of the BGC1. So we say that, and there are BGC2, there are potassic also. So we propose that they are derived from the reworking of the TTG crust in the Proterozoic time. So implication of this would be that BGC2 terrain sodic TTG gneisses are the remnant, because in the BGC2 we also get some of the things of the BGC1. So remnants of BGC1 which are left over after reworking of TTG crust during 1.7, and the potassic gneisses are the reworked product. We have also worked on the amphibolites of the BGC2 terrain, and we have classified the amphibolite rocks of this part mainly into three groups based on field occurrences and the chemistry. One group they are occur as dikes. They represent pre-rift phases. Some mafic volcanics occur as isolated, unassociated with any sediments. So we call them, they represent the opening of a sedimentary basin, Mangalwar sedimentary basin. And third amphibolites, they occur intercalated with sediments. So this could represent the syn sedimentary volcanic phases. So these are some of the findings that so far we have done, and these are some of the complexities that we have tried to understand over the last couple of years. Thank you.
Thank you, Professor Mandal, for an excellent talk. So we have time for questions.
Yeah, sir, in the gneisses, the geochemical signatures of gneisses, you have displayed strong positive lead anomalies and even ZR and HF positive anomalies. And I guess for that you have considered enriched oceanic plateaus to be subducting and remelted as a subduction signature. But why are we not considering the melting of the oceanic crust and then interaction with the continental crust to further elevate the lead and the ZR-HF condition?
There could be many possibilities, but you see these basalts, they are enriched in LiLe and many other elements. So more judicious model would be that to melt a enriched source rather than a depleted source and then enriching by contaminating through crustals. Enriched oceanic crust means more type of, no, it may not be that much. Normally oceanic crust, they are depleted. So to get an enriched oceanic crust, normal mob type crust is difficult proposition. So उससे बेहतर proposition तो प्लेटो होगा और YB type of basalts होगा.
Professor Mondal, of
Yes.
course, I don't know, maybe
Yes.
I may be wrong.
Yes, yes.
Because you are dealing with the banded gneiss complex.
Yes, sir.
The fundamental gneisses are the basic gneisses.
Yes, yes.
So it has undergone metamorphism, probably 2 to 3 stages.
Yes,
of course, metamorphy experts
yes.
are here. And what I find is that you are trying to decipher the parentage or the
Yes.
protoliths
Yes, yes.
based on your chemistry.
Mhm.
But it has been metamorphosed, it was subjected to a lot of metasomatism later,
Yes,
in fact a lot of sodic metasomatism, potassic metasomatism, in the crustal level. So how your chemistry can work to infer all this,
And for that reason, we have to use chemistry in a very, very judicious way and rely only on the faithful elements, which will not be very much moving around and all those things. That we take care. These are the standard procedures in chemistry for such works.
Sir, I have a question. So the mafic enclaves are very interesting. So what is the mineralogy of these enclaves?
They are
which you
now
think?
all amphibolites, hornblende.
So hornblende. But you think that these are the parts of the oceanic crust which has been subducted to that depth. So do you not think that the metamorphic mineral assemblage would be something different?
No, all metamorphic mineral assemblages are all changed. But mineral assemblage change, that's all there, because all these are highly metamorphosed. But we are relying on the trace element, some trace element chemistry, which can give us clues about the protolith, about the magma.
Okay, no, I was thinking because these are undigested parts, so this should have the mineralogy of the depth where it was melting.
No, undigested in the sense that they were not melted.
Any question from the other room, the youngsters? No, thank you, Professor Mandal.
Okay, thank you.
I am giving mic to Dr. Ram Mohan to proceed.
May I request Professor Devdas Ray to present on a review on Indian Cratons in terms of magmatism, metamorphism, and
it has to be put in the forwarding slide, backward. A very good afternoon to everybody. I'm really honored to be present over here and say something about my topic. This not. This is geochemical signatures of Indian Cratons in terms of magmatism, metamorphism, and metallogeny. Actually, what I want to say that I dedicate this talk to my students from Sharojit, who was my 1984 batch, to Arnab or Shubhojit. Of course, Bishwajit is there, Malay Mukul is at IIT Kharagpur, Ovijit is at Malay Mukul at IIT Mumbai, and all that. So what is more important in this particular topic, what I have experienced through my fieldwork all through these years, along with my students, that every time I see or I observe to any fieldwork area in the Indian Cratons, we find complete association of igneous, metamorphic, and in certain cases sedimentary rocks. And of course, metallogeny is significantly associated with all these. So what I realize, it is my experience, and what I realize that every time you analyze, you try to analyze, you try to understand, there must be certain geochemical signatures which are actually taking place. This is just a dedication, Fathers of Geology, a tribute to the pioneers. So you find there are different fathers from from James Sutton, and metamorphic petrology, Escola, igneous petrology by Bowen, because when I studied for the first time evolution of igneous rock by N.L. Bowen, I was literally lost. So magmatism, metamorphism, metallogeny, and interrelationship. How do I proceed? Definition of magma, as you must be knowing, actually you all know about it, but we consider it as a molten rock material which is produced in bulk quantity. This is essentially silicate in composition, but it is not only silicate, there are other components, Na2O, K2O, MgO, FeO, and every time all these rocks which are produced, somewhere it is rich in K2O, somewhere it is Na2O, and sometimes it is FeO and MgO when it is when we are considering about basalt or gabbro, and sometimes it is only rich in CO and Al2O3 when we are considering about anorthosite. And definition of metamorphism, whenever we talk about metamorphism, we say that any parent rock of any single bulk chemistry may undergo changes by the influence of pressure, temperature, or both, and or chemically active fluid, thereby bringing mineralogical, structural, or both changes at a time. So the igneous rocks, what we have, they are being subjected to metamorphism, or the sedimentary rocks that we have. So there is the same chemistry, you know, whenever metamorphic changes are taking place, these are isochemical changes, but whenever we talk about metasomatism, there must be certain other compositional entities. When we talk about serpentinization or migmatization, I am very much interested about migmatization because my thesis area was in Purulia, and first I learned these migmatites from my sir, Dr. Chittaranjan Bhattacharya, CB sir, Chittuda, popularly known as Calcutta University. And when we found migmatites in Purulia, I got interested because such a huge change, the paleosome, nucosome, the neosome, all these things reflect certain amount of chemistry. So definition of metallogeny, we know that about the metallogenetic epoch. So everywhere, if you go all throughout India in different cratons, you find gold, you find chromite, you find manganese, you find iron, you find copper in Shingbhum, in Aravallis, in Dharwar. And in Dharwar in particular, there are different metamorphic belts. When we made our fieldwork in Dharwar, we saw Baba Budansi's belt, Holenarsiputsi's belt, and all these. So I was feeling very happy that I could find even in India, everywhere I go, I find the signatures of all these three. So this is chemistry actually. We are all very much accustomed to this table. So we find that there are different types of lithophil, siderophil, chalcophil, atmophil, organophil. All these elements are distributed in the periodic table. So whenever we talk about chemistry, actually, when we studied the chemistry, when I was a student of IIT Kharagpur, Professor Ashok Mukherjee told me that every time you study any metallogeny, you have to study metal paragenesis, sulfide mineral paragenesis, pyrite, pyrrhotite, chalcopyrite, chalcocite, and all that. Whenever I was studying metamorphic petrology under Professor Shishishin, he told me about petrographic mineralogy depending upon the greenschist phases, amphibolite phases, granulite phases. You find that there are the certain mineral assemblage. But I started with, when metamorphism, different types of zones, that is chloride zone, biotite zone, Scottish Island. I had a wish to study Scottish Island. Now I am 72. I don't know whether I will get the chance to visit Scottish Island because he was the first person who made me interested in metamorphic petrology. All these Scottish Islands, Barrovian zones. Thank you, sir. So this is tectonic map of India, simplified mainly from GSI. You find the distribution, the Aravalli shield, the Dharwar shield, the Bonai, Mayurbhanj granite, then Shingbhum shield, all these shields, everywhere, the signatures are there. And whenever you study all these together, this is Dharwar Craton, so you find there are different types of granite body. I have an interest in granites also because whenever I studied Reed's book about granite controversy, then meditations on granite, I thought I should also think something about granite. So I have some little contribution about granite. I have seen almost all the granites of India. Erinpura granite, Shinghum granite, Bundelkhand granite, all the granites, close-bed granite. It's very close to this particular place. So what I have seen, that you can always meditate on granite as well. So if you meditate on granite, you get the entire signature of geochemical signature that has been taking place, or that had taken place on the surface of the earth. And all these things are happening below the surface of the earth, because we know the interior of the earth is chemically layered. As the interior of the earth is chemically layered, it is very much obvious whatever magmatism, whatever volcanism, whatever metamorphic imprints that we see, actually it is a reflection of the geochemical signature. And we are very proud that India, our country, is so much so endowed with geological formations all throughout these geological ages, especially the Cratons. When I studied the book by plate tectonics by Condi, there was a map. There everywhere in the map there were certain pink colors which show the oldest group of rocks: Australian shield, Canadian shield, Indian shields. Then there are different color shades in terms of pink. Then Kadapa, then Gondwana, and all these different colors. So there were changes. This is geological and mineral map of the state of Karnataka, almost very similar to Dharwad. You find there are different types of granites. There are different types of Chamundi granite, close-bed granite, eastern, then greenstone bed, older peninsular gneissic complex. There are BGC, banded gneissic complex, and there are different types. And these are, if you find, these are the minerals: bauxite, chromite, gold and copper, iron and manganese, and as also limestone. So this is the Aravallis. When I visited, I made field work in Rajasthan area along with my students all through these years. When I first visited the area along with my Professor Dr. Kritin Naha in the Alwar belt, it was my interest to take my students to that area for the first time. When I took them to the field in Rajasthan, I was very much interested about the disharmonic folding. Actually, the disharmonic folding is nothing but a reflection of the chemistry. You find the calcilicate rock, sometimes it is tremolite marble, sometimes it is actinolite marble, sometimes it is, yes, I'm just covering. So every time there is a change in the chemistry, these are all different Cratons. As you find the Shinghum granite, and actually our famous Bowen's reaction series, these are the chemistry behind it. The normative minerals, whenever you analyze actually through the normative minerals, and this is from Mihir Bosch's book, there are different types of igneous rocks. You find the distribution of SiO2 is different in case of anorthosite, and in case of granite is 71.30 to 50.28. And whenever SiO2 changes, all others are changing. This is the second page of that. Peridotite is SiO2 is 42.26. So it is the guiding force: silica, acidic, then basic, then acidic, intermediate, basic, and ultra basic. So all these changes, these are different types of chemistry that we are using for understanding the geochemical signatures. And this is the Scottish Island, as I was telling about it. This is metasomatism, magmatites, the change in chemistry because external fluid is coming and invading the rock. So all these structures are being produced. So these structures are also the geochemical signatures. And these are some, whenever metamorphism are taking place in calcilicate rocks, these are some important equations. So antigorite, dolomite, and forsterite diopside. I am thankful to Shimontini, who was giving her maybe the first lecture on this platform. She was talking about phenocryst. She was talking about olivine. All these are igneous rocks, but these may be the products through the metamorphic activity in the calcilicate system. This is the ore genetic process. You can very well understand. And this is actually a combination of different host rock and common minerals. And whenever you see any metallogenetic deposit, you must be knowing there are wall rock alterations. What I feel wall rock alterations are nothing but the chemical changes that are taking place below the surface of the earth in such deposits. These are all alteration, argillic alteration, silicic alteration, advanced argillic alteration, and all these together. So what I find, conclusion, hydrothermal alteration is a crucial exploration tool offering insights into the mineralization environment, ore forming processes, and economic potential of deposits. But actually it starts from the magmatism, then in metamorphism. This is definitely a thank you. But before you do this, I put this slide for you. This is acknowledgement to Ministry of Earth Science. This particular slide is taken from the Ministry of Earth Science. Actually, I cropped it to a certain extent. It was written over there. Do you know that the active volcano is present in barren island? But as because it is magmatism and all that, I thought this question, any question, the question mark keeps you through the lava.
Thank you, Professor, for making in time. Any questions? 2 questions we can take. First from the research scholars from the other room. Anybody from the other room? Yeah, they can speak. Simple matter. So anybody from here? Thank you very much, sir. Now make a request Dr. Rohit Pandey to speak about diamondiferous lamproids from the Bastar Craton.
Pointer. This is for forward? And forward, backward, and this is the pointer. Thank you. A very good afternoon to all of you. So, today I am going to present geochemical and isotopic evidence for the diverse metasomatic process in the formation of cratonic lamproids. So, let us begin with the diamonds. Diamonds are actually one of the most fascinating gemstones, and it have a quite good link with India. When the first diamonds were discovered from the Kimberley, people were not even believing that diamonds can be found other than Indian continent. And it was regularly, for the many years, it was sent to India to get it confirmed that whether it's really a diamond or not. And the diamond have been even defined in the earth charts in the Kautilya. This I have taken from the Ministry of Mines Twitter handle page, where they have clearly, where in the Slokas 2, it has been mentioned that there are some material which can be cut by in its own. Probably that is the reason that the Vajra, which stands for the Sanskrit and the diamond, and have the similar name Vajra Karur, which is very famous kimberlite field. In Arthas Kautilya too, various trades of diamonds have been defined, and the Ratna Parichanam word has been utilized. Earlier, it was believed that diamond can be found in the, as a primary source rock in the kimberlites only, but in the argile, when one of the most producing, diamond producing body has been found to be lamproid, then people have started looking for the lamproids too. In totality, these are the 3 domains where diamonds and the primary igneous rocks are associated: Vajrakarur, Panna, and the Nuapada lamproitic field. The Nuapada lamproitic field is a part of our current study actually. So the lamproids, they are actually the true blue exotic rocks which are volatile rich. It is formed of very rare minerals. There are some minerals like japite. There are some minerals like priderite. Priderite has been named after the very famous petrologist Rex Prider. And these minerals have been reported very commonly in the lamproids only and some other ultrapotassic rock types. it has a very exotic geochemical signature. It is characterized by its ultrapotassic, perpotassic, peralkaline, and these combinations have been reported only from the lamproids only. It occurs in a very diverse tectonic setting. There is a lamproid which is known as an orogenic lamproid, and it has been marked as a post-collisional activity, signature of post-collisional activity. And some anerogenic lamproids have the typical OIB or the convecting mantle signature. The xenoliths, the lamproids are rich in xenolith, which has been served as a probe to mantle, windows to mantle. And it has been defined on the basis of two, that orogenic and anerogenic in general. So what are the major bottlenecks? And that is forming one of the major objectives of the current study. So various models are there for to explain the metasomatic origin of the lamproid. The one is the recycled continental material, that something has been recycled into the mantle which has caused the enrichment of depleted lithospheric mantle by metasomatic melts, some small scale melting of Horsburgite with readily fusible assemblies like maride, mica, amphibole, rutile, ilmenite, diopside, which has been brought out by your African xenoliths in kimberlite, partial melting of ilmenites, and so on. So there is no common consensus about how the exact enrichment in lamproids has occurred. That is one of our major objectives. Another is, what is the exact source of these lamproids? Whether the SCLM is the main contributor or it has been contributed by the convecting mantle signature. So this is the broader geological setting. These are the different lamproids and kimberlite locations starting from the Vajrakarur, Narayanpet, Ramadugu, Krishna, we have Tokapal, Khadka lamproids, Siddhi, Majgwan, and so on. And this is the current study part where you can see the lamproids occurrences in the Darli Munda. This is our main study area, Darli Munda lamproid field, Kamli Dadar, and Amli Dadar. The main current study is focused on the Darli Munda lamproids actually. So a paper came in 2018 by M. Santosh et al. And they have reported that Darli Munda as one of the oldest lamproid from the peninsular India. And they have dated it as a 2.2 gigaannum. So that forms another very important objective of our study, because as such no 2.2 gigaannum lamproitic or alkaline activity have been reported from the Bastar or nearby area. The nearby areas including Sakri lamproid reported by Chalpati Rao et al. They have reported 1.1 ages, and earlier worker like Sahu et al. They too have reported 1.1. So we wanted to further assess whether it's really a new event or having some other problems. So these are the field occurrences. This is field occurrences of Darli Munda lamproids. It's quite altered in nature. Even in some of the locations, you can pluck samples by your own hand. So we have tried to collect the most freshest possible samples. And these are the same pit, excavated pit, which was dug by actually the state DGM in the search of diamond. And the M. Santosh and the earlier workers, they too have collected some samples from the similar locations. Coming to the petrography, as I already told, it has been quite altered. So as such, primary mineralogy of these lamproids is entirely lacking. What we can see, the preservation of the texture, the typical inequivalent porphyritic texture of the lamproids which is visible. But these are actually the olivine pseudomorph. Olivine has been converted to some secondary minerals. The typical lamproitic texture, and at places we are getting high Mg patches, which are actually the reflectance of the alteration, but which are forming the phlogopitic mat in and around the overall texture. To further confirm, as EPMA and other such mineral-based study investigations was not possible, so we did some XRD, we did some Raman petrography, and what we could find that these are the representation of secondary minerals. For example, olivine has been altered to our lizardite, and the phlogopite has been altered to vermiculite, and so on. With such alteration, one of the very important things is to assess whether the post-magmatic alteration has obliterated the geochemical signature. To assess that, we have plotted different HFSCs and LILE with reference to zirconium, and what we have found, though the LILE has been leached out from the system, but HFSC was quite well correlating with the zirconium, which attests that these post-magmatic alteration have not that much affected the primary core geochemistry of these rocks. And the isotopes and other LILE and HFSC-based diagram plots to suggest that crustal contamination has also not affected in the totality our samples. To further being assured whether it is a direct reflectance of lamproitic geochemistry or not, as the first signature is have to be potassic and ultra-potassic, but it was having very lesser percentage of potassium, only 0.1 to 0.5% of potassium was present. So we have taken some other elements which are quite immobile, and it is quietly well overlapping with the lamproitic field. With the previous study of the Sakri lamproid, with this previous other global lamproids, it was very well overlapping, and with similar to the previous Sakri lamproids, we are also not getting any major troughs which are indicative of our crustal contamination like niobium, tantalum or titanium troughs. They were also not occurring in multi-element spidergram. The quite fractionation of olivine and other titanite bearing phases are also reflected in terms of their MgO fractionation index. Now, when we have also dated one of the rutile of these lamproids, and we have found the ages of around 1.009 million years. Though our error is quite large, but it is again very similar with the previous reported errors by Chalpati Rao et al. And Sahu et al. And Santosh et al. Actually haven't measured the isotopic signatures of these lamproids. And the TDM ages of these lamproids are even younger than the emplacement ages what reported by Santosh et al. So it is not possible to have that 2.2 giga NM ages, as the TDM age, depleted mental model age, can't be younger in comparison to our emplacement ages. Coming to its geochemical signature, its trace element signatures and trace element ratio signatures, and our tectonic distribution plot suggests it's of anerogenic and a typical OIB-like signatures, which is also reflected in several various plots like cerium by lead and cerium and many others. When we have plotted its isotopes, what we are getting an EM1-like signatures, and it was quite well overlapping with the other Mediterranean lamproids which have been reported as a hallmark post-collisional lamproitic activity. And the similar signatures was also overlapping when we have plotted osmium with the arc or some other post-collisional signatures. So in totality, we are getting an OIB-like signature. We are getting isotopic signatures of EM1 and enriched metal, or some where it can be concluded that some ancient oceanic crust was involved in the genesis of these lamproids. So we propose a model that earlier it was involvement of some ancient oceanic crust, then it got enriched in the form of mantle metasomes, and in totality, when it melted, it has generated the lamproids, Darlimunda lamproids in particular. We are also getting some carbonatic metasomatism signature in the form of this superchondritic ratio of zirconium by hafnium, which is consistently higher than 40, titanium by uranium ratio, and some strontium ratios too. Nearby Sakri lamproids too have been reported as a carbonatic metasomatic signature. So it have a complex metasomatic signatures which involves both our OIB, which involves both that ancient subduction part and as well as the carbonatic metasomatism part. The texture is relict. The earlier ages reported by M. Santosh, we conclude that it's a xenocristic age and it can't be the true representation of Darlimunda ages, and that part I have already explained. This paper has been published in Precambrian research, and we have utilized various trace element ratios to confirm our observations, which can be found out. With the permission of chair, and I would also like to take this opportunity to pitch, though it has been approved by Talat Ahmed sir, but still we want to pitch it so that it can be further properly get to know. Sir, बस 2 मिनट में मैं इसको खत्म करूंगा, 2 minutes में. So the theme which we are proposing is actually magmatism, metamorphism, and mineralization. Focus on the geodynamic evolution of the Indian shield. Our tentative dates would be 24 to 26. It would be convened by myself and my other colleague, Dr. Amiya Samal, and joint secretary will be Gulab Gautam. Of course, would be taking overall mentorship of my mentor Chalpati Rao and Rajesh sir. And you can, to join our mailing list and to get update, you can mail us on mmbhu2026@gmail.com. So the location would be Department of Geology. It is very well connected with the airport, with roads, transportation, and even with the water routes too. So this is our conference venue. We have 2 different large halls. Like we have Mahamana Hall, which have the capacity of more than 300 participants. We have one IC Pandey Hall too, which have the capacity of 100. So parallel sessions can too organize at our place in BHU. So we have plenty of accommodation options too. Not that much cozy what ESSO-NCESS is providing us, but yes, it's university accommodation. So we have LD guest house, university guest house, faculty guest house, and recently many mega events like RDS has taken place in our university, advances in mental petrology too, various workshop too has been organized in the past. So I welcome you all in the land of Baba Viswanath, Ganga and BHU. Kindly save the dates, and I'll be taking questions on.
Yeah, thank you, Rohit.
Thank you, sir.
Very nice presentation. So any quick questions from the students?
Sir, state DGM actually have reported a few diamonds nearby Nuapada lamproitic field. And we are also getting in some of the lamprofiers low Mg, high Mn ilmenites, which are actually the indicative of the dimer indicators. And recently, we have actually taken a project by NMDC where we have analyzed huge, around 2,400 grains kimberlite indicator minerals, and that there too, they are getting G9, G10 garnets, which are a peculiar hallmark. So maybe in near future, they are indicators. So maybe in near future, they will be getting some diamonds in that.
Okay, Rohit, just one quick question. I'm just confused. I mean, you're getting subduction signatures as well as enriched mantle signatures. Exactly what kind of setting, geodynamic setting, are you thinking of?
Sir, actually, the isotopes is hinting towards that some ancient oceanic crust was involved, which has enriched that mantle. And the OIB2, that is the convecting mantle part, the lithospheric mantle, which is convecting part, that too have contributed in totality the genesis of these lamproids. So overall setting is actually the interplate setting. And these are actually the hallmark of some anerogenic lamproids, and similar anerogenic lamproids were multi-stage enrichment, where the enrichment's causative factor from the different sources has been emitted from the other parts of the world too.
Now, what about the potassium? Where are you getting that from?
Sir, actually it is quite altered. So potassium lamproids have to have that ultra potassic, more than 3% of potassium have to be.
Where is that source? Where is the source of that potassium? That is what I'm asking.
Where is the source?
Where did you get the potassium into the sublithospheric mantle, let us say, or wherever your source is, into the lamproid? Yeah.
Mostly, sir, metasomatic and due to subductions.
So the source has been metasomatized by,
yes,
that's
yes.
what you're saying.
Yes, sir. Yes, sir. Yes, sir.
Hi, Dr. Rohit, an excellent talk, and I'll certainly save the dates for the next conference. I'm particularly interested in the osmium isotopic figure that you showed. I'm just curious, is this the bulk rock separate, or because it's extremely difficult to get osmium isotopic signatures from any crustal material?
Yes.
And a bulk rock se to shayad aur bhi mushkil hai. So did you separate some magmatic minerals, or this is the bulk rock signature?
It's a bulk rock actually, and yes, I agree. A lot of erratic output was there, erratic results were there, and we have actually analyzed many samples, but we have included only
the ones which make more sense.
Yes,
because in such oceanic settings, even the carbonaceous material will interfere extremely with the osmium isotopic signatures. So, yeah, nice work. Thank you.
Thank you, sir.
Many hands raised. One more last.
Sir, in the map, I observed that all the lamproid locations, they are more or less located around the Proterozoic basins. So any specific reason for that?
Actually, one paper is there by Ashutosh Pandey and Chalpati Rao, where they have, gathered that all these things, all these lamproitic activities, they are parting a single chain, and it has been formed due to the plate reorientation, amalgamation of rhodinia, and they are occurring in a that you can refer that paper in Lithos, where they have discussed in detail about why it is occurring in a single chain and domain like that. No, it's not exactly about the Proterozoic basins, because nearby your Siddhi, nearby your Majgawan lamproids, such Proterozoic basins are not nearby. Yeah.
Okay, thank you. I think we'll close this talk now. Thank you, Rohit.
Thank you, sir.
Actually, it's already 1:10. We'll have more interactions during the lunch, requesting everyone. Now I request Dr. Saumi Chattopadhyay about Kutch Alkaline Suit of
Hello.
Good afternoon, everyone. Yeah, it's audible. Hello. So, good afternoon, everyone. Yeah, in previous session, Shimandini already introduced the Deccan LIP with us. So, I'm not going to detail about this. It is one of the largest magmatism that happened in the Indian subcontinent. Its diverse nature contribute entire spectrum of the geosciences, like from the study of paleontology to geotectonicism, geophysical studies, and also the petrology, and even in economic geology also. So being a petrologist, it is very much important to understand the nature and evolution of the source mantle for the generation of this massive eruption. And in this study, I am trying to understand the source mantle characteristic during the time of Deccan magmatism. This is the aerial extent of the Deccan volcanism. As Shimandini told previously, the earliest derivatives of this Deccan is restricted in some particular places, like the Kutch and Mudvara, Sarnu Dandali, etc. And my study area is the Kutch, which hosts different type of volcanic rocks. If we see their chemistry, among these, I only focus for this study only the alkaline rock, as we understand the nature of the mantle evolution or the source mantle characteristic. The reason behind choosing the alkaline rocks, first of all, the alkaline rock has been considered as the early phase magmatism in any type of plume-related magmatic event. Secondly, the Kutch alkaline rock particularly contains some pedotite fragments as a xenolith or xenocrest. So that indicate the ascent rate of this alkaline magmatism should be high. And if the ascent rate is higher for this magmatism, they can freeze the original mineralogical and petrological signature of their source mantle. That's why I'm choosing this alkaline rock. These are the field photographs forming a columnar outcrop in the Kutch area. If we see the petrographic characteristic, we can divide these alkaline rocks in three broad groups. First of all, this nephelinite. This rock composed of olivine phenocrest, which emitted in a fine-grained ground mass, and this ground mass comprised of smaller olivine, clinopyroxene, some FETI oxide, nepheline, and also some perovskite also. The second group is the basonite. The main difference is that the basonite also contains the olivine phenocrest as well as some clinopyroxene phenocrest also. And the main difference is that their ground mass comprised of the similar with the nephelinite, but main difference is that it contains some plagioclase within their ground mass, whereas the nephelinite is completely free of the plagioclase in their ground mass. And in case of third group, it is basically a trachybasalt. It also contains the olivine phenocrest, whereas their ground mass composed by plagioclase, FETI oxide, and also very few alkali feldspar also. Interestingly, these two alkaline rocks only contain the mantle fragments as a xenolith or as a xenocrest. Coming to the petrography of the xenolith, and this is coarse grain rock rather than their comparison with their volcanics, and this is composed of spinel, orthopyroxene, olivine, clinopyroxene, and represent as a spinel lertzolite, which represent the subcontinental lithospheric mantle beneath the western Indian continent. So to understand the geochemical characteristic of the volcanics, of the alkali volcanics from the Kutch area, we use some trace element ratio, and it clearly it clearly shows us the nephelinite is more alkaline in nature rather than the trachybasalt and the basonite. In case of chondrite normalized RE pattern, the nephelinite and basonite, means the xenolith bearing alkaline rocks, are more enriched in LRE in comparison with the trachybasalt. And similarly, in case of primitive mantle normalized multi-element spider diagram, there are some important features we need to note. First of all, the positive niobium and tantalum anomaly for all these rocks. It is an indicator of alkaline nature. Secondly, the negative potassium and lead anomaly. That means the crustal that indicate that they can discard the crustal contamination within this type of alkaline rocks. Their positive TI anomaly also indicate the depth of origin should be higher for this to generate this alkaline magmatism. And their HRE content, if you see the HRE pattern, it indicates for the xenolith bearing alkaline rock that they may have generated from the garnet bearing source, whereas if we see the dy by ytterbium ratio for both of these rocks, the trachy basalt showing the lower concentration, maybe spinel have played some important role to generate this trachy basalt. To further constrain the source, we use some trace element based discrimination diagram where the nephelinite and basonite clearly follow the mantle trend and showing the similarities with the ocean island type of basalt, whereas the trachy basalt didn't follow this trend. In this diagram also show that they have originated from the different sources. And in the left-hand side diagram, it also said the nephelinite and basonite shows the plume-related ocean island basalt type signature, whereas the source for the trachy basalt may have modified or may have showing some presence of the enrichment mantle component. We use some petrological calculation also to understand the composition of the source magma for this alkaline magmatism, and for this we have used the method proposed by Hertzberg and Asimov as a primal 3 and the primal calc 2 by Kimura and Ariskin. And by this calculation, it says us this alkali magma has been generated from a garnet peridotite source, and the mantle potential temperature during the magma generation was so high, that is 1308 to 1524 degrees centigrade. Also, it says that the magma generation takes place at a very great depth, that is approximately 2 to 4 GPa depth, and the degree of melting, they are product of very low degree of mantle melting, that is 0.4 to 4% of. For all this calculation, we have choose the high MgO bearing rock for this calculation, and the high MgO bearing rock in this case is the nephelinite. We also calculated the oxygen isotope from the phenocrystic olivine of every alkaline rocks. And when we plotted against the olivine composition and also the bulk rock composition, the nephelinite and basonite showing the similar Day-Lectino ratio with the mantle olivine. That means it can say that the source for the nephelinite and basonite may be the similar with the asthenospheric melt, whereas the trachy basalt showing the different character and it contains the higher Day-Lectino value. That means they have generated from the different source of this magma, and the possibilities for the source for this trachy basalt may have the subcontinental lithospheric mantle. Secondly, it may be their source has been modified by the crustal contamination by the crustal material, or they have generated from the subduction modified source. To further ascertain the source more precisely, we combine it with some radiogenic isotopic data also, and when we plot the neodymium concentration versus strontium for these three rocks, the nephelinite always show as their geochemical part, bulk rock geochemistry also shows, and their stress element also shows the similarity with the primitive mantle or the bulk silicate earth, whereas the basonite is plotted towards some depleted, showing some depleted nature, and the trachy basalt showing the enriched component should be the source for this trachy basalt magma. We use some bivariate diagram to understand the process also. And for this, when we plot the strontium isotopic concentration against their MgO percentage, the trachy basalt follow the assimilation fractional crystallization. But the assimilation product should not be the crustal component, because as the trace element pattern show, the rock is devoid of any type of crustal contamination. And if you see the Day-Lectino versus K2 concentration and their strontium isotopic concentration, it also discards the possibilities of the crustal contamination. That means the assimilation product should be the subcontinental lithospheric mantle, that is basically a spinel peridotite, as their trace element distribution shows, then the rock may be generated from the spinel peridotite field. For the understanding the nature of the mantle condition due to the during the Deccan magmatism, we also perform some thermobarometric calculation using the mineral chemical data from the xenolith also, and the bulk rock geochemistry data from the alkaline rocks also. The xenolith represent, when we plot the PT in this diagram, the xenolith represent the very shallower depth that is stable up to 70 kilometer depth, whereas the alkaline rock has been generated very greater depth that is up to 100 kilometer below the, sorry, I'm just finishing. Below the Earth's continent, northwestern Indian continent, and the trachy basalt magma may have generated by this magma when it coming out to the surface and contaminated by the presence of subcontinental lithospheric mantle or somehow between this area. So these are the mantle scenario at the onset of Deccan magmatism from this. So thank you. Thank you, sir. Thank you, sir.
Thank you, Swami, for making in time. Any questions?
Yes, sir.
Not a question, just how far of your rocks from the Kala Dungar complex?
Sir, it is
because Kala Dungar also is very.
it is almost 150 kilometer. That is in the central part of the Bhuj, and around Bhuj 70-80 kilometers.
I have not correlated that alkaline rock with your rocks.
With Kala Dungar? No, I was not in Kala Dungar part. So I am concentrated on the xenolith bearing rock. That's why I am taking this alkaline magma.
First of all, I have to tell that I really enjoyed your talk.
Thank
It
you,
was
sir.
presented in a very understandable and interesting manner. I just have two comments on this. One is, you know what is the potential temperature of the asthenospheric mantle?
Where the magma has been generated, if we plot this temperature to the, if we
Right, so
project
you-
this temperature to the
Now, what is the temperature of the asthenospheric mantle? The potential temperature just below the, just say derived from the part that is just below the lithosphere. That is approximately 1300 degrees centigrade.
Yes, if
So
we-
the type of temperature you have requires 150 almost degrees centigrade
1500.
higher, right?
Yes, 1500.
So without addition of some heat from the lower mantle in the form of a plume, it will be difficult to get. I mean, you can just comment on it afterwards.
Yes,
The second thing is, I know you've done, not sure how these programs actually work, but do you know the phase diagrams that actually pertain to the generation of extremely undersaturated silicate melts from, say, a mantle of pyrolytic composition? Do you know what the phase diagrams tell
We
us?
see the phosphate, silica, and for the case of nephelinite, so we need to incorporate the nepheline silica system. So to generate the nepheline.
You still
within-
can't generate. You still cannot
we-
generate.
we need to consider.
The melt you need to have is a Larnite normative melt. That is the first melt that you need to get. And as far as I know, the only way you can get a Larnite normative melt is if you have a CO2 saturated mantle.
Yes.
Now, do you see any carbonate?
Yes.
Because in the phases you didn't mention the presence of any carbonate.
Yes, sir. I'm just telling you. I'm not showing in my presentation, but when we calculate the, when we match our composition with the experimental carbonated peridotite melting, it generated, and we also performed some alpha melts modeling, and it shows the 0.3% carbonated flexolite has been the source for the generate of the nephelinite. We performed for this nephelinite and basonite, and it is the product of nephelinite was the very low partial melting product for the melting of a carbonated lead-solite. And we perform it, and we this is actually published in my paper. I'm not showing this diagram also in the presentation.
It answers my question. I was wondering why you didn't mention it, because
yes,
the phase diagram relationship is what would actually constrain it. I mean, it is very easy to get lost in isotopes and trace elements, but the fundamental thing is to understand the phase diagram.
Yes, sir.
So you should have mentioned that because
sir,
it would have made it very easy to connect. Okay, and anyway, once again,
Thank
very
you for the
enjoyable.
suggestion. Yes, I just forgot. I just missed it.
Can you just show the thin sections? You just showed a photograph of thin section.
Yeah.
Yeah, Amal.
Not from a single picture, actually I have taken some overlapping picture and then we stitched it. Same slide. Yeah, this is from the same slide. This is a mantle phenolate entrenched within the alkaline matter. Spinel lepsolite. This is spinel. There is some re-equilibration texture also. In case of the core composition, the color is means petrographic. That is normal body color. That is normal black. This is basically aluminium bearing component. No, this is not. No, this is not magnetite. Yes, the re-equilibration part is showing the magnetite. Chromium number is 0.1 to 0.3%.
Interesting to learn.
Yes, sir.
Excellent plot. You have input of continental crust. Continental lithospheric. Now,
In case of practical, sir?
generate such ferroan origin with derivation from mantle, some sort of mantle signature is there.
Yes.
So obviously the magma composition is significantly matching. From there, how you can generate an olivine which is 30 more percent phosphorus? Does it involve significant amount of fractional crystallization?
There is two possibilities. Actually, I am working on the modeling section and I didn't show it here because I am not finished yet. Maybe this, but what I have started, if this trachy result is the product of fractionation from the nephelinite, because nephelinite is the primary, showing the primary signature, but there, after iteration, their HRE content is showing not similar pattern. That means we are not the product for the fractionation of nephelinite or primitive alkaline magma. That is the
Thank you, sir. Now I will request our director, sir, to hand over the memento to the chairperson, to Professor Rajesh K. Srivastav and Dr. M. Ram Mohan.
and you just helped me to
Hello, check. Hello, check.